that. Good afternoon, everyone. I was waiting a bit. Commissioner Mall will be along shortly. So welcome to all of you. And, oh, look at you. A whole cast of panelists. Justin, maybe I'll start with welcome you and welcome all of you and let you all introduce yourselves.
Thank you, Chair Reeves and members of the Commission. For the record, I'm Justin Iverson. I manage the groundwater section here at the department. I've come with a group of folks from our Harney Basin study team, our basin study team, both department folks and folks from the USGS. Well, let's see. This agenda item is our annual update on the Harney Basin process. We're required by rule to come and provide an update to the Commission every year. And since we've done this for a couple of years and my spiel hasn't changed too much, we thought we'd do something a little different and get members of the study team here to reprise a set of what we dubbed as lightning talks that we gave to the community out in Burns last October. So we're at kind of a pivot point in the study where we're moving from dominantly data collection to data analysis, and we provided kind of a summary of what we've done over the last couple of years that were given by members of the study team. So this is a subset of them, not everybody, but in the hour we have, we thought we'd provide for the Commission a flavor of what we're doing from the people that are doing it, and we can either introduce ourselves all at once, or as we go down the line, each person has a 5 to 7 minute lightning talk, and thought was we could introduce ourselves as each person speaks. Is that fair?
Sure, that's fine.
Could you do both? Do both, sure. Okay.
Hi, I'm Amanda Garcia. I'm with the USGS.
I'm Jordan Beamer, hydrologist with the Water Resource Department.
Hank Johnson, USGS hydrologist.
Jerry Grondin, hydrogeologist, Water Resources Department.
Hi, I'm Steve Nierick. I'm also a hydrologist with the USGS.
Welcome.
Okay, so I'm going to lead off, give a quick background again as to why we're here. I'm going to talk about new groundwater permits issued within the Greater Harney Valley Groundwater Area of Concern, or the GIVGAC. Going to give a quick update regarding groundwater level data, and then the bulk of our presentation is going to be, as I just mentioned, 5 lightning talks from the scientists to my right here. So I'm going to, again, go through this pretty quick because we've talked about this the last couple of years. Real quick problem statement in one slide is that water levels in the Harney Basin have been declining relatively precipitously in the past couple decades after being stable for quite some time. So that's a hydrograph from 1955 to today. From a number of wells right in the middle of the Harney Basin, that inset map up to the upper left. And in a nutshell, the problem is we're pumping out more water than is coming in. Therefore, we're pumping storage out of the system, and that's causing water levels to drop. So back in, 2014 and 15, we were talking about this issue. The Commission adopted some updates to the basin rules in April of 2016. Among other things, they were intended to protect the existing groundwater users, the senior users. They also initiated a basin-wide groundwater study to help us develop a more detailed understanding of what's happening in the basin. We also wanted that to be a commonly understood conceptual model for the basin. And one way in which we're doing that, and which is written into rule, is we've jointly with the Harney County Commissioners convened a local groundwater study advisory committee that we've met with quarterly since 2016 to share what we're doing and take input from them on their understanding of the basin. And lastly, I put in as a bullet that these rules, again, among other things, ask us to report annually to the Commission. So we've done that beginning of the year for the last few years. That annual report specifically needs to include what's happening with any new groundwater permits we've issued within the groundwater area of concern, updates regarding water level data, and staff recommendations, if any, We don't have any at this point in time other than hold the course, and we noted that in the staff report. So we've issued one permit in 2018. It was kind of a legacy permit. The priority date was September 12th of, excuse me, I take that back. I guess I didn't write up there exactly what the date was. I believe it had a 2012 priority date. It predated our work in the basin. There it is at the top, thank you. And so essentially that permit came through. We reviewed it under the standards of the day in 2012. We noted that the well that they wanted to authorize as a point of appropriation had some well construction issues, and we proposed to deny the permit until or unless that well was brought up to construction standards. It went on to an administrative hold for a number of years. The applicant got that well squared away in 2018, and we continued issuing that permit. So that was not a permit that was issued within the special provisions that were set up in the new basin rules. That was, again, kind of a legacy permit that happened to work itself through the system this year. All right, and that's all I've got on new permits. Again, just that one. There's a table in your staff report of everything that we've done since 2016. So,
Is it okay?
Commissioner Corn. Yeah.
Is there any more of those hanging out there like that maybe in the next couple of years? I mean, I was just looking at my thing here, the ones that you've done, and they're
Yeah.
kind of coming in at different levels. This is a small one compared to some of them that have been here.
Yes. Commissioner Reeves and, or excuse me, Chair Reeves and Commissioner Corn, that's a really good question and one I should have anticipated. I don't know off the top of my head, but I'll get back to you on that.
Okay.
All right. All right. One quick slide on groundwater level data. This is a table that I've updated annually for the past few years. Basically just shows on the far right-hand column where we were in 2014. I'll draw your attention to that third line down where we had 23 wells that we had quarterly water levels at to show trends. And 2 of those wells we had continuous recorders installed. At the time in 2016, we felt like that, among some other information we had, was substantial evidence in order to promulgate the rules that we pushed through. But again, we had agreed to expand our monitoring network and improve and update our understanding. So over the past few years, we've basically got tenfold the number of wells, 231 that we've been measuring annually, and another, 100 of those that we monitor quarterly. Of the total number of water level measurements that WRD staff have made, we've been ramping up from 2015 through 2017, and then you'll see we're tapering off. So we're finding wells that are tracking together that are basically telling us the same thing about the same region, and therefore we've been dropping those duplicative wells, if you will. And that's also, so we're spending a little less time in the field, and we're also transitioning to the analysis phase. So just wanted to throw this map up there, not because it's real readable on the screen, but because you've got a copy of this as an attachment or appendix to your staff report, so you can take a look at the spatial distribution of where things are a little bit closer there in the staff report. And then just to reiterate again, we started in 2016, initiated this cooperative study. We established the Groundwater Study Advisory Committee. We've met quarterly with the Study Advisory Committee since then, and we transitioned really to our data analysis phase late 2018 till we are where that yellow star is now at this data analysis effort. We're continuing to get input from the Study Advisory Committee, so we're bringing our near final products as we make them, our maps and tables, to the Study Advisory Committee and getting their input at this phase as well. In 2020, the draft report will go out for scientific peer review, and we're looking to publish at the end of 2020. And then within a year of that time, we will be reconvening the RAC to reassess the management options out in the basin. All right, just wanted to mention, I've already mentioned the cooperators, the WRD and the USGS dominantly with our local study Advisory Committee. We have also contracted a number of studies from the State Department of Geology, and that includes both geologic mapping, detailed mapping of quadrangles, regional mapping, and rock sample collection to tie everything together, as well as they handle the LiDAR surveys in the state. So we've gotten a lot of detailed elevation data from them as well. Crane School and PSU are involved in work. Our partners at DEQ are conducting a water quality study out there for domestic water supplies. There's some work being done with OSU scientists, UNR folks, and University of Nevada, Reno Desert Research Institute, and the Nature Conservancy are all working out there on complementary efforts. All right, and then lastly for me, I just wanted to mention I had said that this wasn't our full study team. There are a number of folks that aren't presenting today. Wanted to make sure and get their names up there and acknowledge the work that they've done to add to what we know. And in small text down there, I put a link. I mentioned that many of these these 5 lightning talks plus 3 or 4 others we gave in Burns back in October. Those are all up on the internet. So when this presentation is posted publicly, folks can find that link if they're interested in seeing all the presentations we gave in Burns. You can follow that. So without further ado, I will pass on and let folks describe the work that they've been working on for the past couple of years.
Hello. Again, my name is Amanda Garcia with the USGS. I'm a hydrologist there. And I'm going to talk to you a bit about what we know so far about the hydrologic budget in Harney Basin, specifically groundwater budget. So groundwater budget's similar to your household budget. You have a certain amount of money that comes in each week or bi-week or month or what have you with your paychecks and your dividends and whatnot. You have a certain amount of money that leaves your account each month through different bills that you might have, and the net difference between what goes in and what goes out is the net change in your account. Same thing with the groundwater budget. You have a certain amount of water that comes in, that's called recharge, a certain amount of water that leaves your aquifer system called discharge, and the net change is your change in aquifer storage. So under long-term steady-state conditions, the inflow equals outflow, and your net change in storage is 0. When you have more outflow than inflow under a system where you have groundwater development in addition to your natural discharge from the system, then you're going to have a negative change in storage, meaning that over time you're going to see a groundwater level decline. So here is our 3D diagram of the groundwater flow system in the Harney Basin. We point your attention to the green arrows pointing downward. That represents inflow to the system or recharge. The red arrows pointing upward represent discharge from the system or outflow. And the blue arrows represent direction of water flow within the system. So the primary mechanisms for recharge within the Harney Basin are through upland recharge. Precipitation falls directly on the mountains. Some of that water recharges the aquifer system, some of it runs off into streams and rivers, and some of it evapotranspires back to the atmosphere. Second major component is stream flow loss and flooding on the valley floor. As the streams and rivers flow down to the valley floor, some of that water is lost to the subsurface basin fill. Some of that water runs off to Malheur Lakes and Harney Lakes, and some of that water is used for surface water irrigation and also floods, naturally floods the fields adjacent to like the Silvies River and the Blitzen River during the spring freshet when there's big snow melt and a lot of flow going through those rivers. It overflows the banks often. So these other mechanisms also contribute to recharge of the shallow basin fill. So the main discharge from the basin is through natural groundwater evapotranspiration, or ET. We have groundwater ET that occurs where you have spring discharge at the land surface. There's direct evaporation of that discharge water from spring pools or any other open water from where springs are discharged, and then you also have evapotranspiration of that water when it flows down gradient and is consumed by vegetation along the flow path. There's also groundwater evapotranspiration by plants that are deeply rooted, root down to the capillary fringe, which is just above the water table, or sometimes even down into the water table. This is typically where the groundwater level or the depth to water is less than 20 to 30 feet below land surface. Those plants are called phreatophytes, and they exist across the Harney Basin valley floor. And so that's another major component of groundwater leaving the system. So the ways that we're estimating recharge, we're coming at it from a few different approaches. These incorporate precipitation measurements and modeled precipitation within the basin, evapotranspiration estimates, soils data that's been mapped within the Harney Basin, runoff measurements from several gauges across the Harney Basin, land cover mapping, flood maps that we've developed from satellite imagery, and we're combining all of this information to get at recharge, both spatially and temporally within the basin. Our discharge estimates are primarily through groundwater evapotranspiration, and this is the natural discharge from the system that I'm presenting to you now. Next, Jordan will be talking about the groundwater discharge through agricultural irrigation. So we work, in order to estimate natural groundwater ET, we have vegetation maps across the basin. Where this is where we're looking at mapping the different types of plants that are using groundwater and different densities of those plants within the basin. We're using weather data as well that's been collected at sites and has been modeled. ET data that's measured in other basins throughout the Great Basin. And then we've also field verified our vegetation maps at multiple points around the Harney Basin. So this figure here shows the distribution of groundwater ET. This is our preliminary estimate, where the reddish brown represents the lowest rates of groundwater ET of less than 0.2 of a foot per year, and the dark green represent the highest rates at up to 3 feet per year. So the lowest rates are coming from really sparse shrubland areas where there aren't that many phreatophytes, and the very green areas are like marshy areas, very wet. Oh, sorry, one more thing. The gray represents irrigated agriculture within the basin as well. So those are areas that Jordan will cover in his talk. So I'll give you some bulk estimates across the basin for total recharge and discharge. This figure shows recharge. We have upland recharge estimate of about 120,000 acre-feet per year, and a stream flow loss estimate of 40 to 100,000 acre-feet per year, and this varies depending on how much precipitation and runoff there is from one year to the next. This gives us a total recharge of about 160 to 220,000 acre-feet per year, and this range is similar to the range in previous estimates of about 170 to 260,000 acre-feet per year. These estimates were made in the early 1930s and in the late 1960s. Our natural groundwater discharge by evapotranspiration estimates are ranging from about 190,000 to 220,000 acre-feet per year. And this is similar to the range I just gave you for recharge that we've come up with so far. And it's also within the range of previous estimates within the basin. So our next steps in looking at recharge and discharge are to refine these estimates even further. We have a soil water balance model that we're using to look at the spatial extent of recharge and the timing over the last 35 years. We're also using satellite and measured ET data to improve our estimates of groundwater discharge within the basin. And then we also want to evaluate the distributions of recharge versus discharge so we can understand more of the flow system dynamics within the Harney Basin. So with that, I'll pass it off to Jordan.
Good afternoon, members of the commission. So for the record, my name's Jordan Beamer. I'm a hydrologist in the surface water section here at Water Resources. Thanks for the opportunity to present to you this afternoon. I am here today to present the our estimates of irrigation water use for the Harney Basin study. So Amanda gave us a nice introduction to the basin water budget, specifically the groundwater recharge and discharge, kind of from a natural, undeveloped system. And so I'm kind of building off of her presentation to discuss the groundwater pumping for irrigating crops that's being pumped from the aquifer. So as we kind of zoom in from the basin-wide scale and look at the irrigated fields within the basin, we're really interested in how much of this water is being pumped from the aquifer, applied to the fields. Now, ideally, we would have pumping records that we could use, at every single pumping well in the basin that we could utilize to provide this estimate. Unfortunately, we don't have that type of spatial coverage or, back in time to have a complete picture. And so we end up estimating the use somewhat indirectly, and this kind of shows a diagram of the field water budget, where we have the inputs to the field are primarily from precipitation, and the bulk is from the pumped groundwater applied, via irrigation systems. And then the primary outflow loss is from this evapotranspiration term that Amanda discussed. And so I think it's really important concept for myself, as well as you guys, understand what this ET term means. It's essentially the evaporation of water from a plant surface, from a leaf, or from the underlying soil surface, as well as the transpiration of the plant itself as it utilizes water to grow. And we can use that to, it's kind of the primary determinant of irrigation water requirements and crop water use. So in order for us to estimate pumpage and crop water use across the basin for every single field that's being irrigated, we're utilizing satellite imagery and a model called Metric that was developed at the University of Idaho. It's been used extensively in the western U.S. for doing kind of crop water use, basin water budget assessments. And so we utilize this to look back in time. So we have a historical archive of Landsat data that goes back to 1984, and that allows us to get this historical picture of historical crop water use and evolution through time. And I think a big thanks goes out to our partners at Desert Research Institute, we've partnered up on a NASA ROSES grant, which has really allowed us to implement this technology for the first time at the department. So one of the key components to applying a satellite-based evapotranspiration is having accurate ground-based measurements of weather and crop water use in the basin. Unfortunately, the Harney Basin lacks a long-term agromet station, but our partners at Desert Research Institute, we've worked with local landowners and the Malheur Field Station to install 2 sensors that measure weather and evapotranspiration that we can use to kind of validate our satellite estimates. So jumping into some results, so this is basically a picture of the Harney Basin. You can see kind of the outline of the groundwater study area, and then we've taken the May through September evapotranspiration from Metric, clipped it to the fields, the irrigated fields that are irrigating with groundwater. And so we can see that for 1991, there was about 32,000 acres of fields irrigated with groundwater in the basin, kind of scattered around, a few clusters here and there. And the growing season ET volume was about 58,000 acre feet. We jumped to 2016, and the acreage has increased to about 73,000 acres. You can see large clusters of center pivots, irrigated fields along the Highway 20 corridor, Weaver Springs, Crane Buchanan areas. So a large increase in the development in those areas. And across the basin, the total volume increases to about 150,000 acre feet. And this, just to kind of put that in frame of reference, is about the same volume as Prineville Reservoir. So circling back to the basin-wide water budget that Amanda introduced, we can add in our estimates of the losses, the outflow of water through crop evapotranspiration to Amanda's natural vegetation estimates to get a total discharge of about 300 to 370,000 acre feet. And we'll notice that that is outside, that is larger than the estimated recharge range. So if we think about the water budget, discharge is greater than recharge, this indicates a decrease in storage from the system. So the next steps for my work, we are going to be validating our metric ET results with the ground-based measurements that we've collected from about September 2017 onward. And we also are going to start comparing our ET with the pumping records that we can come across in order to utilize this information to estimate pumping and irrigation efficiency in the basin. And that's all I got. Thanks.
Hello. I'm Hank Johnson. I'm a hydrologist with USGS. And forgive me, I don't know all the formalities. I think it's addressed the commission, so thanks for having us here today.
Don't worry about it. Thank you.
So mine's a little less data-rich than what you've seen from Amanda and Jordan. I'm going to be talking more about a lot of the geochemical work that we're doing in the basin. And some of those data are still awaiting analysis. They're still sitting at labs. So I'm going to give you an overview of the way that's proceeding in our study and how we're going to be using that information. So we're using the natural chemistry of the groundwater, not anthropogenically introduced things like nitrate or pesticides or anything like that. These are natural chemicals that occur in the groundwater system. And we're using them to help clarify flow paths, validating what the water level measurements are telling us. Where's water moving from and how's it getting there? Where's it going and how's it getting there? Estimate the travel time. How long does it take water to move from one place in the basin to another? And that has impacts on recovery, recharge, and things like that. We can use the natural chemistry of groundwater to identify mixing, different sources of water as they move into the valley bottom, which is pretty heterogeneous. It's not really well-defined aquifers that we're seeing in there. Kind of visualize it as kind of a big bowl of sediment that mixes together, and so the chemistry helps us identify different sources that are moving into that basin bowl. And they're useful for calibrating numerical models, which is phase 2 of this study that we really haven't talked about yet, but Steve's going to get to the numerical modeling portion of that later. So why does this matter? Our precipitation and recharge is largely occurring in the uplands. The demand for water in the basin is largely occurring in the basin sediments in the valley floor. So understanding how water is moving from recharge to use and discharge areas is really critical. We have two regions in the basin really that have high precipitation. The dominant recharge occurs in the north and in the south, in the uplands there, with modest amounts of recharge elsewhere in the basin. So we have long flow paths from recharge to discharge in use areas. And really only 3 main streams that are bringing water into the valley bottom. And again, I mentioned the sort of vertically and horizontally heterogeneous basin fill deposits that make it difficult to sort of track if you think of if you're sort of visualizing a layered aquifer system. That's not something we are conceptualizing the basin fill as having. So you can't really track from one depth to another across the basin. So the chemistry helps disentangle what's going on out there in the basin fill. So we're using samples from springs, from naturally discharging springs, samples from wells that owners in the basin are allowing us to access, and streams during low flow. So this would be base flow samples that there's no runoff entering the streams during those periods, so it gives us an integrated snapshot of the groundwater system upstream of that area. We're using four sort of large groups of tracers. The first being common ions that you're probably familiar with, like chloride, calcium, sulfate, sodium, things like that. A little less familiar might be carbon-14. It's used for dating in archaeology a fair amount, baskets and charcoal bits and whatnot. There's carbon-14 that gets entrained through atmospheric gases and can be used to date old groundwaters. We're using tritium, which is a naturally occurring isotope of, it's a radioactive naturally occurring isotope of hydrogen. Occurs naturally throughout all history, but humans introduced a big slug of tritium in the atmosphere in the 1950s and 60s with nuclear testing. And that's still decaying. Tritium has a half-life of about 12.3 years, and so we're still seeing tritium, residual elevated tritium from the 50s and 60s that we can use to get estimates of recharge time. And probably most esoteric of all, we're using naturally occurring stable isotopes of water. These have actually been our workhorse. They're inexpensive to analyze, easy to collect, and so we have a huge database of stable isotope data that's being used to help identify source and mixing in the basin. So real quick snapshots of some sort of the summary so what's here. Along the eastern side of the basin, where's the mouse? You can use that. I should have had an inset map here, I apologize. So this is the town of Crane, here's Burns over here. The Crane-Buchanan Highway runs along here. This is the Virginia Valley, Malheur Gap area, and we have indications of pre-modern water at depth and fairly shallow in these parts of the basin. In the Sylvies recharge zone coming southeast out of Burns, this is the second largest stream system in the basin, the largest draining the Blue Mountain uplands in the north. We see indications of modern recharge, as Amanda described, leaking out of the stream bottom and losing into the aquifer system. When we drill deeper and we look at wells at depth, we see older water at depth or indications of older water at depth. So it seems like we have sort of this modern recharge signal that comes and lays atop some older water that's sitting and filling the basin. And we can see that. Here's an example of don't worry about what these units are, just know that sort of these higher numbers are younger and these older numbers tend to be older waters. And as we look at depth as our wells get deeper, we can see we tend towards older water, and these are all samples from the Sylvies area. And then this southwest portion of the basin is pretty sparsely populated, not really well developed, and we're still kind of working out what's going on out here. The expectation is that the recharge is low, the use is pretty low, but the water's likely going to be fairly old that we're seeing coming out of that area. I'll turn it over to Jerry at this point.
Madam Chair and Commission, for the record, my name is Jerry Grondin. I'm a hydrogeologist with the groundwater section here at the Oregon Water Resources Department. And I'm one of the two co-leads for the department on this study. And we're working in cooperation, with our USGS partners in doing this study. The agreement between the USGS and the department was signed in September of 2016. Our work plan was completed in December of 2016, so we've been working in earnest since December of 2016, trying to get everything together to meet our deadline for having the report completed by the end of 2020. Now, before I launch into what I'm doing is on the technical side of this investigation, I need to acknowledge two other people from our department and their contribution to this study. First is the other co-leader from the department, Dark Boschman. Unfortunately, he couldn't be here today for good reasons. His daughter was born on Monday. So Dark is putting together really the foundational information for our investigation. He's putting together the geologic framework. And so he's looking and compiling all the information that existed historically in previous reports and the ongoing mapping that's occurring now to put together the superficial geology. And then he's looking at the well data to put together the subsurface geology, and then looking at the geologic structure in the basin. Additionally, we're having contributions from Jonathan Lamarche. He's our hydrologist out of the Bend office, and he's looking at the surface water hydrology, looking at surface water flow, but most importantly, where the streams are measuring what are the stream gains and losses. And that helps us understand what the hydraulic connection between groundwater and surface water is and how efficient that connection is. So on this particular map, he went out and did some seepage runs and documented where the streams are losing water or where streams are gaining water in that interaction with groundwater. So building on their two shoulders and the work that Hank is doing and so the first thing I'm doing is I'm taking the geologic information that Dark is putting together and assigning hydraulic properties to those geologic materials. And in some of those geologic materials, we may have different types of materials, but they may have similar properties. And most importantly is, what is the permeability? How well can water move through that material? And then also, what are the storage properties? How well can that material store? Is it fine grain and there's not a lot of storage? Or is it, fairly coarse and water can move in and out of it efficiently and there's a fair amount of storage? The other thing is, one of our main diagnostic tools is, as we do this investigation, are groundwater levels. And these groundwater levels really help us understand, what are the hydraulic connections between different geologic materials? What's the hydraulic connection between the uplands and the lowlands? What's the hydraulic connections across geologic structures? And so then we also use this to look at groundwater trends and groundwater flow paths. As we look at the groundwater trends, we look at how does the system respond to natural stresses. That could be, if we get into a drought period, how does the system respond to that versus a wet season? And then how does the system respond once we introduce human activity and start extracting water for different types of uses? And we look at that on a seasonal basis, and then we look at it on a long-term annual basis. So this is a hydrograph for an area where, in the basin, where these two wells are fairly close together. And when they originally were drilled, they have very similar water levels as a starting point. One well is open to the shallower part of the groundwater column, and then the other one is open to the deeper part of the groundwater column. Now, this groundwater column, it's saturated continuously. But with time, as water got developed, the water at the deeper depth got depressurized, and we're seeing this downward trend. Now, in the upper part of the system, we're also seeing a downward trend, but it's not as acute as we see in the deeper part of the system. And the seasonal fluctuations in the shallower part of the system are not as dramatic as they are in the deeper part of the system. So we look at this kind of data to kind of put together the story of how does the system respond to the various stresses that are put on it, and what can we anticipate if, as development goes on, or if we make some other adjustments to that groundwater use. Now, we have our fingers on about 2,700 wells as we do this project, looking at the geology. We have about 1,600 wells where we have aquifer property data. And then out of all those wells, we have, as Justin previously noted, about 231 wells where we collected water level data to put together our water table map. In addition to the data that we're collecting, the Harney Watershed Council is collecting water levels from about 102 wells. And then we have, in 2018, reported water level data that are related to our permit condition wells. And out of those 194 wells, 17 of those overlap our project wells. And then in addition to that, we have out of the national database identified springs of about 2,500 springs that we can reference for control for putting together our maps. So out of those, 231 wells that we measured for the water for the potentiometric map, about 112 of those through 2018 we've been measuring quarterly. We're reducing that down to 105 here in 2009, and then again the Watershed Council's measuring their 102 wells on a quarterly basis. And then out of those quarterly wells, we have about 24 wells that we have continuous recorders measuring water levels on an hourly basis to help really refine and capture some things that you can't capture on a quarterly basis. So from the 231 wells, we can put together a water table map. Now, this map that is before you today is based on much fewer wells, water levels collected in 2016. We're still working on the 2018 map. But looking at this map, we can see that in the blue area, the blue outlined area is the groundwater recharge along the Sylvies fan that Hank just mentioned previously. And then in the red enclosed areas is where groundwater is discharging to the Donner and Blitzen River to the south and to the Silver Creek area to the northwest. When we add the information that we collected by the seepage runs by Jonathan LaMarche, we can say even more about the groundwater surface water interaction. Again, the red enclosed areas where groundwater is discharging to surface water, and then the blue is where surface water is seeping back into the ground and recharging the groundwater. If you look at the northern end on this map, you can see that you have these red areas right next to the blue areas. And what's happening is that in the upland areas, groundwater is discharging to the streams, it comes out into the valley onto the alluvial fans, and then seeps through those alluvial fans back into the groundwater system. Now, with the development, when we look at the water level data, because we have data that goes back to the 1930s, and if you look at the data from the 1930s to the 1970s, groundwater levels were relatively stable. But from the 1970s to the present is when the system was being developed, and we start seeing the groundwater level declines. And these enclosed areas kind of show the declines in the different areas. So up east of Burns, we're seeing declines of 20 to 40 feet. In the eastern side of the basin, we're seeing declines from 10 to 30 feet, depending on where you are. In the Weaver Springs area, in the center of that map, we're seeing declines of 25 to 80 feet. And then up in the Silver Creek Valley to the northwest is where our shallowest declines have occurred. And so, so with the development that's occurred since the 1970s, we are seeing a groundwater level response to that. And as we do our investigations, we're trying to understand how that's all working, and what can we do to better manage that resource in the long term. And with that, I'll hand it over to Steve.
Okay, thanks, Jerry. My name's Steve Gingrich. Again, I'm a hydrologist with the U.S. Geological Survey. Thank you for having me here. I'm going to talk a bit about the sort of the final phase of the project, more like the phase 2. We're going to represent this whole system with a groundwater model. So phase 2, why do we do this? A groundwater flow system can be synthesized so you can understand the whole system using a numerically based physical model. And, modeling is a common method to understand complex physical processes. They use it in, show up here, aerodynamics and heat flow and electrical systems and mining and so on and so forth. So you can turn the physics of groundwater flow into a model and use it to test what might happen in the future. You can play what-if games with a big system like this that you can't really test or build in a laboratory. So we'll go back to our diagram of the kind of the basin here that everyone has kind of used to talk about their parts of the system. And so a groundwater model, when we understand the entire system, we can turn it into a series of numerical equations that can solve groundwater flow through that system. So what we do is we divide the basin up into these kind of evenly spaced blocks where each block has its own individual properties of geology, permeability, hydrology, things like that. So we use the information that DARC is collecting with his geologic map. And we could kind of divide this up and say, okay, we have the simple geology of the basin fill in yellow and the uplands in red, and we know the properties of how water flows through each of those types of rocks. So we can divide the aquifer up into a system like this. We can look at the hydrology of the system, so we've got the blue line there. So we can represent the streams that we talked about where we're measuring gaining and losing flows. We can put that in the model, represent the streams here. We have springs represented by the blue squares here where water might be discharging from the aquifer. And then we have green represents some wells. So Jordan's estimating how much water might be coming out from these wells, used for irrigation and so on. So we can put those in the system and represent them as well. So we get ahead and we build this model that physically represents the aquifer system out there. And then once we build this, we can start to what we call is calibrate the model. So we run the model, we look at how the water levels in the model react, and we adjust the parameters, things that we see out in the field, until we can match the measured water levels that Jerry's been collecting and others have been collecting for years. And so we do our best to have the model represent the real data that we collect out there. And so we match water levels, we can match the stream discharge that Jonathan LaMarche has measured. And this is usually the longest and hardest process of any model building is the calibration, that you can adjust the properties in such a way so you can do your best representation of what we're seeing out in the real world. And then once the model is calibrated, that's where the real strength comes. You can use the model as a tool to understand the system better and play sort of what-if games. So here's an example of a system on the left. You've got a water table, and maybe the groundwater near a stream is discharging to that stream and allowing water to flow into the stream and away. And you've got your recharge on the surface and discharge from the stream and ET and so forth. And then you can look at a development condition where we put in a well, pump that well, so you're going to reduce storage. And in any system like this, if you take water out of the system from a well, you're going to have to, that loss of water is going to be made up somewhere. And in this case, it's made up by less water discharging to the stream. And in a case, you could, if you draw down water enough, you could have stream water kind of reversing flow and entering back into the aquifer and recharging the aquifer and thereby reducing stream flow. So if you have a case of a single well and a small system, there are things you can do. You can measure streams and you can look at it, and maybe you can figure it out without a model in a very simple single well, single aquifer type system. But we have a huge area. Harney Basin is, I think, about the size of the state of Connecticut. It's giant. It's got thousands of wells, all kinds of diverse geology. So you can't just sit down with your pencil and paper and figure out what wells are going to do or what's affecting each other. So that's where the power of the model comes in, where we can look at the three-dimensional hydrologic characteristics and the three-dimensional geology and plug in certain scenarios and see what's happening. So here's an example also used in the state from a model built in the Klamath Basin that some of you are probably familiar with. This is a case where the question was, well, what if we put in a well or a series of wells in this certain location? How is that going to affect stream flow nearby? And so hydrologists, have studied the area and already figured out that, the stream flow is affected by groundwater. So the model doesn't necessarily tell you something that you didn't know, but it can help confirm what you've already figured out, or tell you the impact of what you might suspect. So here's a case, again, where we know that putting in wells will affect groundwater. So we blow it up a bit. So the circles represent, we put in a well, pump it at a certain rate, you're going to get drawdown of the water table. That cone of depression will spread and eventually intersect where it intersects surface water streams. And then the colors along the stream there show where flow in the stream would be decreased as an example of putting a well in this area. So that's a thing you couldn't figure out without having a model to understand the 3D complexity of the system. So that's sort of what we're shooting for. We've just really begun to lay out the framework of that model. We're still a few years away. But we've kind of built a preliminary model that's helped us guide some of the sample collection, some of the groundwater water level areas to look at, some of the stream flow collection. We've been able to recommend where to go measure that based on some of the preliminary model that we've done already. So as the next few years go by and when we finalize our basic understanding of the groundwater flow system, we'll be able to fine-tune the model to match that and eventually have this as a management tool that the state can use to play these what-if games of how you could change pumping or move pumping or decrease pumping, or what happens if recharge decreases or vegetation changes, something like that. All those things can be put into the model, and we could get an insight into what might happen far into the future. So I think that's the end there.
Thank you. Wow. Been busy. Questions?
I have one question.
Yeah, Bob.
In a previous conversation, we heard a suggestion that the basin might not be all freely interconnected. There may be some of it in which there are some barriers that may change or influence the drop as a relative flow, and perhaps from wells and others. And I'm just wondering if there's any indication of that, or if you're going to be able to have that kind of refinement in your numerical model.
Well, from what we've seen so far is based on the chemistry that we've collected and the water level records that we have for years and the aerial distribution of water levels, we don't see a lot of, like hard barriers or compartments like you would be thinking. Most of the deep wells, we seem to see shallow wells that are affected by that, showing some sort of, communication. It might not be very direct, or it might take years for that, for that effect, to propagate to the shallow area. We do see, because of the vast distance, maybe pumping in the far west Silver Creek Valley might not affect, something out in Virginia Valley, which is, 60 some miles away or something like that. So I think the more separation would be due to the distances and some of the geology from those far distances, rather than, individual compartments, saving this well from affecting a well, 2 miles away or something like that. So. Okay.
Yes, please.
So, as you look at this, is there, in wet years or in high flow during the winter or whatever, is there ways to increase recharge through recharge wells, is there techniques and methods? I know Eastern Idaho, they've had, they have areas where they recharge. Of course, it's more of a volcanic area. Are you seeing any potential for that to accelerate recharge to help to offset some of this?
Madam Chair, Commissioner, what we're seeing is that in the area where most of the development is happening is a fairly low permeability area. And so what's happening in that area is, as they pump some very significant cones of depression are forming that persist from year to year, rather than you pump it down and then it kind of recovers, and then you kind of step down. If you think of the Klamath Basin, as they were, pumping it since 2000, you kind of get the stepwise decrease in an area. Whereas in the Harney Basin, where most of the development is happening, you get these large cones, steep cones that don't extend out very, very far. And so that would suggest that these wells may not readily, if you recharge through some of these wells, you're not going to see the benefit that you would in some of these higher permeability zones where it's like watching a reservoir rise and fall. That doesn't mean that they can't have some benefit, but it may not be in the same order of magnitude that you would hope to see in some other areas in the state. Now, there's some areas like in the Silver Creek Valley where it's kind of a more volcanic terrain, and so there we are seeing kind of things rise and fall together. There may be there's not as much development there, but in that neighborhood, it might be more receptive to a recharge project.
Questions, other questions?
Yeah, only one.
Yeah.
Really have a lot more, but all over the slides, it was unpublished data, subject to revision, please do not cite, which, having worked with USGS, I understand at some level. And at the same time, wait until 2021 to be able to take what you've learned, what you're learning right now, and then make decisions around it is not really satisfying in some ways. Are you finding things now that you feel like, wow, this is different, this is important, this is not a part of the narrative? Are there things that you're finding in your research that you feel tempted to put out there even though it's not yet peer reviewed?
All right, I'll take that one, Chair Reeves, Commissioner Mole. I don't want, I guess that the question you're asking is somewhat mitigated by the fact that since 2016 and these new rules, we aren't issuing new permits that didn't already have an application in. So there's been a limited number of new applications that have come in. In the transfer realm, previously we had a big bowl homogeneous model that's kind of being refined to a big bowl heterogeneous model, and we're starting to change how we process transfer applications and requests that come through. So we are using that information. I'm going to balance that with, we came out to the community and had a number of public meetings in 2015-16. We agreed on a time frame for this study that is pretty aggressive. And I think that you heard Jerry speak to that we've committed to this 2020 timeline, and I don't know that we've done that in the past with these types of studies. So we're doing everything we can to meet that timeline. We've committed to pulling the Rules Advisory Committee back together within a year of having that publication out. So we want to balance having the best available information in a published piece of work that's been peer-reviewed and isn't going to, change next week or next month, while at the same time understanding that some folks are more eager than others, to tell you the truth, out in the basin. So we're trying to balance all interests, and hearing from the folks in the basin, some saying it's too fast, some saying it's too slow. Perhaps we've hit a good compromise on the timing of what we're doing.
If I can add something to get to your answer, Madam Chair and Commissioner, to get to your question, as an example, I've been meeting with the USGS the last couple of weeks to talk about the water table map that we're producing for this report. And I showed you the graph where you saw that separation of the shallower part of the water column and the deeper part of the water column depressurizing and kind of separating. And so the question of putting together the map for the area was, well, how do we represent that in a map form? And so we originally put together a single map to show it. And over our conversations the last couple of weeks, we've concluded that we really need to have two maps to show what's happening shallow versus what's happening deep. So that's kind of, an example of how, we didn't want people to lock onto a map when we realized, we could better tell this, to explain with two maps rather than one.
Great. So that's pretty recent understanding? That was the...
Yeah, we came to that conclusion last Friday.
That's pretty recent. Great, thank you.
Other questions, comments?
You mentioned about reduced stream flows with declining water table. Are you seeing that measurably when you compare comparable runoff years to prior comparable runoff years? Are you seeing decreased stream flows, or was that more in the modeling that you would expect that?
I can answer that. Well, that was just kind of an example of what a model can do. For the Harney Basin, it's kind of unique that most of the stream flow is occurring in the uplands, and the pumping and use is in the basin floor. And I would say there's very little indication that stream flow is being decreased by pumping, just because of the unique situation out there where stream flow comes down and empties into the basin and then sinks into the bowl of, sediment in the floor. So there's not much stream flow in the basin floor to be affected by nearby pumping. So the biggest thing we're seeing there is just the drawdown, affecting, shallow wells that are going dry, or deep wells that have to be deepened, to get more water, or more expensive pumping costs, because the electricity of pumping to higher level, things like that. So for a basin-wide study, this is one, like I say, where we see the indications are there's not much stream flow being affected by the pumping.
The basin's unique where nothing really flows out. It just flows into Malheur Lake or Harney Lake, where in most basins it flows out to the ocean ultimately.
Exactly,
So
yeah.
that makes it a unique basin.
So, I mean, there are indications that some groundwater might be flowing out of the basin in one of the gaps, but we're still trying to figure out if that's the case and how much that might be, if it's significant or not significant. We don't really know yet, I guess.
We did have one more question. Oh,
Well, mine's entirely curiosity.
I got a quick data question. I think, I can't remember whose presentation it was, but when you looked at, I think it was 1969, 32,000 acres in agriculture and 50,000 acre feet of evapotranspiration, and then when you went from that to about 70,000 acres in ag land and 150,000 acre feet, so the rate of evapotranspiration went up pretty significantly, it seemed. Is that it just got hotter? Is that the kind of agriculture or the kind of pumping that's occurring? Is any conclusions from that, or did I even read that right?
Madam Chair, Commissioner, I think the rates themselves vary slightly year to year. I think, if you did the math, that in in the 90s, the rates were slightly lower and they've increased. And we're also, right now, we've done kind of a more intensive analysis of separating out those fields irrigated with surface water, those fields irrigated with groundwater. And there's areas where there's both a surface water influence earlier in the year and groundwater later in the year, and kind of trying to partition out the volumes and the rates kind of by source type and by year.
But isn't most of the new development alfalfa where it wasn't before? It was more meadowlands that was flooded.
Yeah, I would say for the irrigated, groundwater irrigated areas, center pivot
So
alfalfa.
more heavy water need?
Yes.
Okay, that makes sense.
Let's do one more, and then we should probably move on. What was next? Mike, if you need to ask a question. so you go.
Now, what I was curious about is, a long time ago, back in 1996, there was actually a proposal to drain the lake because of 3 years of heavy rainfall was flooding there. And I'm just wondering, with the analysis you've done, Jerry, can we sort out the kind of these long-term weathering patterns from the impact of the wells and how that plays for a long-term management strategy?
Madam Chair, Commissioner, there are, where we do have the long-term water level data, you can see some climatic influence. What's interesting is down in the Weaver Springs area, we have a long-term pair of wells, and the water levels pretty much kind of almost track the lake level, and when the lake was flooding back in the mid-'80s, late '80s, it kind of went up. But then as development progressed in that area, it just kind of went off the cliff and it just separated itself from whatever the lake was doing. But where we can, in different instances, see a climatic influence in the dry cycle versus the wet cycle.
Thank you.
It's more of a comment. Great work, you guys. I think it's fantastic to hear the level of detail that you're putting to this study. And I think from a department standpoint, making decisions based on science is so important. And my question would be, I know when I first started on the commission, we had some other areas we talked about needs for doing additional groundwater studies, so we can really look at that connection between groundwater and surface water. So my question is, and notwithstanding the great work you've done in this one section, and it's not done yet, where are we for future studies so we can keep track and really, I imagine the community is very responsive to this kind of data as you make decisions whether or not to approve wells. And I think that's so important for all of us in the future. So where are we in the future with that?
Okay, Chair Reeves and Commissioner Fott. So we do, well, let me start here. We've been doing these cooperative basin studies with the GS for, well, I think since the late 80s. This is our fourth large one, so the Deschutes, the Willamette, the Klamath preceded this. We're working on this one now. Typically 5-ish years, assuming a steady budget, or at least maybe that's as quick as we've done a conceptual model report is what we're doing right now, followed by a couple of years for a numerical model. And yes, excuse me. And we've got the resources, the capacity, both the staff and the funds to enter into these cooperative cost share agreements with the GS to do one at a time. I guess I'll answer your question in two parts. So we have a number of areas where we would like to have this more holistic understanding. I think that I know that the Walla Walla subbasin, which we've talked about before in previous items, is probably our next highest priority, and we've tried to start laying the groundwork there, and we were kind of collecting more data on the side, but eventually when this all wraps up and our resources are freed up, that's where we'll move, and we've got a priority list of about 12 basins or subbasins that we're looking at down the line. So we've had several conversations with a bunch of different interested parties about that, and how long is that going to take? Well, decades. And could you do it faster? I don't want to get too far into the director's office side of things, but we've got a piece of that made it from the agency requested budget to the governor's requested budget for another study team. So both staff in the groundwater, surface water, IS support positions, as well as funding to enter into these agreements with the USGS, with the Oregon Department of Geology, to do two studies in parallel. So that would presumably cut the time in about half. And then we had other stakeholders come back and say, well, what could you do with more? And we've had conversations about, well, could we You've heard today mostly about the data collection and some real preliminary results, and we're really getting into the meat of the analysis where we're overlapping all the various pieces of information we have to create an entire picture. And we've really had to ramp up our data collection, as you saw on the second or third slide that I put up there. What if we ramped up our data collection statewide now, and then when the scientists come in, they've got that rich data set and a much more long-term time and spatially intensive data set to work with. So we've been developing strategies around what would that look like, and could we cut the amount of time in half again. So we've been thinking about it and planning for it.
Well, thank you, and again, great work, team.
Thank you, Justin, and really thanks to all of you for taking the time to come, excuse me, and present to us today. It was very helpful, and we do appreciate it. So I'm sure we'll be hearing more about this.
Yeah, indeed.
Thank you.
Thank you.
So I want to take, just for a minute, talk about the next two agenda items, because they're related but different in terms of how they will be handling them. The next agenda item is C, which is a Klamath Basin update, and it's focused on a proposed approach that the department is recommending in a set of proposed rules. That agenda item will be like a typical agenda item for us. There'll be public comment, we can have back and forth with staff that are presenting or with commenters. At the close of that agenda item, we're going to take a break, and then we're going to do the next agenda item, which is actually a rulemaking hearing. It's a formal process, and it is creating a record for a formal process. When we do that, we're not going to be acting as the typical commission. We're going to be acting as a hearing officer, so we'll be taking comment, but we won't be having interaction with people who are commenting. The people who are commenting during that agenda item are here to put material on the record. So we're just functioning as the people hearing that. There are two different, for those of you who would like to address the commission in either of these, either in the first agenda item, which is a more typical agenda item, or the rulemaking hearing. For the first agenda item, the more typical one, if you could fill out one of these sheets and hand it to Jen or Cindy, who are at the end of this table. If you'd like to if you have something that you want to be in the rulemaking record, do it in the second agenda item, and fill out one of these and hand it to Jen or Cindy, and you'll be able to make comment then. So, did I leave anything out?
May I ask a question?
Yes.
In the rulemaking session, are we allowed to ask clarifying questions of a comment? We simply are witnessing and listening.
We're witnessing and listening.
Thank you.
Mm-hmm. Yeah, but in the next agenda item, we're just being the commission, and there can be back and forth
Okay.
as usual. Yeah.
Yeah, our signal silence for a while.
So, did we lose? We lost a couple people, but let's go ahead and get started because we're a little behind on the Klamath Basin update.
Chair Reeves, members of the commission, for the record, my name is Ivan Gall. I'm the administrator for the Field Services Division. With me, I've got Justin Iverson, manager of the groundwater section, and Mike Toma, senior hydrologist or hydrogeologist with the department who works with us in the Klamath Basin. Today, I wanted to cover kind of a broad range of time and issues in the Klamath. Wanted to touch on some of the water management background down there in the basin and try and leave you with a sense of some of the complexities that we deal with there. Do a brief summary of regulation of wells and a little bit of surface water over the last several years. Talk a little bit about the Division 25 rule amendment process that we are in the middle of, get you up to speed on where we are with that process there. And then talk a little bit about looking forward for the 2019 and 2020 irrigation seasons and how the proposed rules play into that. At that point, I'll turn it over to Mike Toma, who will take about 25 minutes or so to give you guys kind of a broad overview of the basin hydrology and hydrogeology down there. So stepping back in relatively recent history to 2001, that's when the federal government shut off water to the Bureau of Reclamation irrigation districts projects down there. You may recall the Bucket Brigade down there. It really was widely publicized. Right about that same period of time, the state and the federal government recognized that there was going to be some serious water management issues down there. And so we began our cooperative study with the U.S. Geological Survey on the basin hydrology there, I mentioned in the bottom bullet. Listed species, there's a number of them, and in this particular case, 2 of the species are in Upper Klamath Lake, the short nose and Lost River suckers. They're also in some of the Lost River system there as well. And then you have an anadromous fish, the coho salmon are listed on the Klamath River below the lake. And both of those species, of course, depend upon water, and so there's a bit of a back and forth as to which species are entitled to it. We work with 4 federally recognized tribes in Oregon, the Klamath tribes, and then in California, the Hupa, Karuk, and Yurok. Federal litigation has been swirling in the Klamath Basin, going back to the 2001 shutoff, where there's a continuing litigation over a takings issue there. And then in more recent years, 2 of the California tribes have filed in federal court with respect to ESA issues, looking to get the Bureau of Reclamation to manage releases from Upper Klamath Lake into the Klamath River in order to better benefit the anadromous fish there. Bottom bullet there, of course, gets back to what I had mentioned earlier. We completed a cooperative study with the U.S. Geological Survey in the Upper Klamath Basin. Now, that's in both Oregon and California. The Basin Hydrology Report was published in 2007 and was followed 5 years later by a model report. And there have been a few subsequent smaller publications since. In amongst kind of that framework of time there, there's been a considerable amount of effort on the state's part, water users, the various stakeholders in the basin, the tribes, the federal government, dealing with a number of water management issues there. Our state adjudication process for the surface water rights, the determined claims there, continues. As I was working through this, I recognized that we had submitted the findings, final order of determination to the Circuit Court back in 2013. So we're coming up on 6 years here in March that adjudication process has been continuing through the Klamath Circuit Court there. There have been a number of settlement negotiations that have occurred and are continuing to occur at some level. The earlier settlement negotiations, KBRA, the Upper Klamath Basin Comprehensive Agreement, have functionally come and gone. The Department of Interior, Alan Mickelson, is continuing to hold meetings with both states of Oregon and California, the various tribes, and water users in the basin, trying to look for some path forward. He has been coming to Oregon and California about once a month for several days for at least the past year now. Mother Nature hasn't dealt us a great hand of cards. The last 6 of the last 9 years, we've had declared droughts in the Klamath Basin. So the actual supply of water has just been short more years than not. And then looking forward to April of this year, the Bureau of Reclamation has been working on a new biological opinion for the project down there, and that will likely have water management repercussions as well as they try and figure out how to split up water between the project, leaving some in the lake for the endangered sucker species, and releasing water from the lake for the anadromous fish coming up the river. Focusing a little bit here on the regulation background. Again, in 2013, March, we delivered the findings of fact order of determination to the Klamath Circuit Court, so that adjudication process has been continuing. In 2014, the Upper Klamath Basin Comprehensive Agreement was signed, so that was a culmination of about 18 months worth of work with state and federal agencies, Upper Basin water users. It carried a lot of provisions dealing with riparian areas, water right retirements, trying to get it up to 30,000 acre feet into Upper Klamath Lake, and had a fair number of provisions there that dealt with groundwater regulation, and that's really the portion that we'll be focusing on here the rest of my talk today. Out of that 2014 agreement, the department agreed to bring to the commission a set of rules that contain provisions from the Upper Basin Comprehensive Agreement. And we did so in the spring of 2015. That was the original Division 25 rules that we'll be talking about here. The Commission did adopt those rules, again, including a number of provisions from that agreement focused specifically on regulation of wells in the Upper Basin there. So for the next 3 years, 2015, 16, and 17, some wells in the Upper Basin were regulated under these Division 25 rules. Those rules, because of the settlement agreement, afforded groundwater users a number of protections. The tribes was effectively calling on less surface water than their in-stream determined claims actually contained. And so there was less frequent calls and calls of lower magnitude during that period during 2015 and 2016. Some of the provisions of the agreement outside of groundwater regulation weren't being met, and so in 2017, the Klamath Tribe started a process where they first made a full call on their in-stream determined claims. The agreement allowed that if all the terms weren't being met. And the tribes then started a process to meet and confer with the other parties. That process failed, and so they petitioned the Secretary of the Interior, who at the end of December there in 2017 published a negative notice which effectively terminated that 2014 Upper Klamath Basin Comprehensive Agreement. Now, going back to our Division 25 rules, when those were adopted, they contained a provision that in the event the comprehensive agreement was terminated, then groundwater regulation within the Klamath Basin or the Upper Basin there would occur under the statewide Division 9 rules, which have been in place since 1988, and no longer would be under the Division 25 rules. And so for 2018, last irrigation season, wells in the Upper Klamath Basin were regulated under those Division 9 rules, and that resulted in a significant increase in the number of wells being regulated. And I'll get to those numbers here shortly. Backing away a little bit from groundwater regulation, I wanted to just touch briefly on some of the other regulatory activities that have been going on. Since 2013, the agency has installed and continues to operate and maintain a number of new gauging stations to measure surface water discharge at a number of points. Some of those gauging stations are very challenging. The Wood River, as an example, is a very low gradient. Sometimes water actually blows back upriver when the winds are right and the lake stage is high enough. So the instrumentation that we have to use for stream discharge there is a lot more sophisticated and requires a lot more labor to continue to operate that properly. The last 2 years, in 2017 and 18, staff focused more water master time, assistant water master time on the Wood River Basin in order to better understand the very specifics of the water rights out there, where the points of diversion were, acres associated with each point of diversion, generate landowner contact information, and then did more and increased regulatory activity there. I wanted to point out here kind of the results of that focused activity. What you're looking at here is a stream hydrograph for 4 years. So this is going to represent 2016, 2017, 2015, 16, 17, and 18. The black stair-stepping bar are the values of the tribal in-stream determined claim for the lower Wood River Valley here. The y-axis on this side is in cubic feet per second. I think that's going from 100 down here at the base up to 450 at the top is the scale you're looking at. But what I wanted to point out here is that the tribal determined claims peak in the summer months here. And so this is when their in-stream determined claims are actually the highest. And you can see in 2015 and 16 during that period of time, stream flow was down in this area here on the order of 175, 200 cubic feet per second. With more focused regulation and landowner outreach and education, during the last couple of irrigation seasons in 2017 here and 2018, you can see the distinct difference where in the previous years we were down here. Now in the last 2 years we've been able to maintain stream flows closer to these determined claim values there. And so regulatory compliance has increased quite a bit. Landowners have a better understanding of the rates that they can divert at, and we have a much better understanding of how to get around the system down there efficiently and regulate accordingly. In the basin last year, there were about 433 surface water diversions that were subject to regulation. This is a very large-scale map. This basin's always challenging to display on a map, but for reference, Upper Klamath Lake is here, Crater Lake is up here. You've got the Sprague River system, the Williamson River system coming into the marsh and then on down, and the Wood River system over here. So, groundwater regulation, wells subject to regulation. So again, as a reminder, in 2017, we were operating under the Division 25 rules. There were about 50 wells that were subject to regulation. Those are denoted here in blue. In 2018, with the termination of the agreement, we went back to Division 9 for regulation, increasing the number of wells subject to regulation from 50 to 140. Those are denoted the blue remains, and then yellow have been the additional ones there. Getting now to the kind of our proposed revisions for the Division 25 rules, I wanted to take a minute and just point out our regulation is based on our scientific understanding of the basin hydrology. Mike will cover that in his talk. Those are all peer-reviewed journals. It's what we consider to be the best available science. And, we understand that we have the statutory authority to regulate groundwater users in favor of senior surface water rights, what we call conjunctive management there. It's been evident, though, even under the Division 25 rules, that water users continue to have concerns about our groundwater management down there. As you're all aware, we've had a significant amount of litigation that's occurred. There were the equivalent of about 4 or 5 lawsuits filed when we were operating with the Division 25 rules. We prevailed in the Court of Appeals with those so far. Circuit Court. They're at the Court of Appeals now awaiting oral argument, which will be in May. So that isn't resolved yet. Last year, when we transitioned from Division 25 rules to the Division 9, we greatly increased the number of wells that were subject to regulation, and the litigation went up accordingly. I think we had 13 or 14 lawsuits related to the groundwater regulation that were filed there. So we wanted to take a different approach. We think it's important to step back and make the staff time, put forward the effort to go down to the basin and continue to do communication and outreach with the water users. It's our intention to hold a series of open house meetings down there and do a lot of listening. looking for feedback on water management and regulation there in the basin. We want to also try and increase a common understanding of how the basin hydrology works. That is at issue. Folks don't necessarily agree with the agency's conceptual model and understanding of the basin hydrology. We're very confident in that, but it continues to stand in the way of really moving forward with the water users down there. So it's our hope to spend some time with folks down there, junior water users, senior water users, the various stakeholder groups, including the federal government and the project there, to look at alternatives for water management and water distribution in the basin. Focusing real quickly here on the rule process, we've already held 2 RAC meetings on the proposed rules. Both of those were in Klamath Falls at OIT, one on January 15th and the second one on January 28th. Both were very well attended. This is kind of the summary table, if you will, of where we've been and where we're going. Again, the top line there, 2015 through 17, where we were under the Division 25 rules with about 50 wells subject to regulation. Last year in 2018, we moved to Division 9 rules. You can see the large increase in the number of wells that were subject to regulation there. None of those bargained for protections from the Upper Basin Comprehensive Agreement exist in the Division 9 world there. For 2019 and 2020, we're proposing to amend the Division 25 rules, effectively repeal everything that was part of the original rules and insert new language in there that would limit regulation of wells that are located within 500 feet of surface water only. And you can see that that drops the number of wells subject to regulation substantially down to 7. The rules have a sunset in there that would keep them in place until March of 2021, would effectively get us through the 2019 and 2020 irrigation seasons. If we can't come up with new rules to deal with groundwater management and regulation, then we would revert back to Division 9, which is where we were at last year in 2018. The ongoing process of the rule amendment is listed here. You can see in early January there, the draft rules were distributed to the RAC, followed by the 2 RAC meetings in January. We're currently in the public comment period. Today will be the February 21st public hearing that you'll be holding after this presentation. I'll be going to Klamath with Mike next week, and we'll be holding a second public hearing again at OIT on Tuesday afternoon from 1 to 3 p.m. And right now we have you scheduled for April 12th, probably a teleconference meeting to consider adoption of the amended Division 25 rules. As I mentioned earlier, if the proposed rules are adopted, we would anticipate beginning this summer and probably carrying into the winter of 2020, a number of open house meetings down in the basin, listening to water management ideas, trying to share our information on the basin hydrology there and see if we can find some common ground to move forward on. So I will stop there and turn it over to Mike unless anyone has any questions at this point.
I just,
Yes, Bruce.
why the 2021 sunset is really just an interim type rulemaking is really what we're looking at this point. Is it just a trial run to see how effective it is, or what is the reasoning on just 2 years on these rules?
Chair Reeves, Commissioner Korn, these are being proposed as interim rules to effectively get us through 2 irrigation seasons. The rules as drafted represent a significant rollback in a regulatory presence to protect senior water rights. And so we don't want to continue that long-term, but we are using it to, again, try and find some space and free up some staff time to go down there and see if we can move the conversation forward to something that's more productive. The agency feels very strongly that we have a solid understanding on the science and the conceptual understanding of the basin hydrology down there. Nothing has changed on that in any way, shape, or form. We're not afraid to litigate, but it's not very productive. And so we're trying to look for a better path forward, frankly.
All right, so for the record, my name is Mike Toma. I'm a hydrogeologist with the Water Resources Department. Thank you for the opportunity to present today. I'm going to provide a kind of basic overview of the Klamath Basin, focusing on the geology and the hydrogeology, and then in the end get to kind of the conceptual idea of groundwater surface water connection and this idea of stream depletion. I want to point out that a lot of the information, a lot of the data I'm going to be presenting comes from these two USGS reports, and these were done in collaboration with the Water Resource Department and the Bureau of Reclamation. It's good that we kind of followed the Harney group, because I think it's fair to say that the ultimate result of that study is going to be something similar to these kinds of reports, a basin scale, kind of collaborative effort to really kind of nail down our best understanding of how things work down there. So just kind of for overview, south central portion of Oregon, the Klamath River then flows through northern California to the Pacific Ocean. The basin as a whole is about 10,000 square miles. Upper Klamath Basin, which generally speaking is everything above Copco Dam, which is located kind of down here, about 8,000 square miles. Ivan already kind of pointed out the Sprague, Williamson, Wood River, and then this here's the Lost River Subbasin. Throughout the Upper Klamath Basin, there's about 500,000 permitted acres for irrigation, with about 200,000 of that being in the project area. And for reference, the project area is kind of loosely defined as this area highlighted in orange, but it's really kind of the large federal projects in the Lost River Subbasin and below Upper Klamath Lake. So looking at water right development over time, again, about 500,000 permitted acres. Prior to 1900, there was about 100,000 acres, and then early in 1900s, 1905, I believe, these large federal projects came on board. This is the project area, and again, kind of a pretty large jump of about 200,000 acres, and then kind of a steady increase of development. Beginning about 1945 or so, you see in green, started to issue groundwater rights for irrigation. And then kind of the last thing to point out is right around late 1990s, basically stopped issuing surface water rights as water was no longer available. Continued partially to issue groundwater rights, but then in 2001, you see that kind of flattens out. And that really comes as I think the department begins to recognize as well as acknowledge the connection between groundwater and surface water. And then after about 2000 I guess kind of the more recent ones, we have some recent groundwater permits issued. A lot of that tends to be in the project area in the Lost River Subbasin. This plot shows the well development over time. So as a well is drilled, beginning in 1955, the department requires that a well log be submitted to the department. So that's why there's not a lot of information before then. And then really just kind of this steady increase in the amount of wells being drilled. And the reason why I want to point this slide out is that when it comes to studying subsurface geology and hydrogeology specifically, a lot of information can be gathered from well logs. A lot of information is provided by well logs. And so the increase in the number of wells drilled over time really represents a significant increase in the geologic and hydrogeologic information gathered. Talking briefly about the geology, it certainly is complex. Most of Oregon geology is. And you have kind of what I'm really going to focus on, the main geologic process for the Upper Klamath Basin is this basin and range process. Older rocks, the oldest rocks in the basin are part of the Klamath Mountains. They're 65 million years old and older. And the youngest are associated with the Western Western Cascades, the Cascade Range, which kind of the most episodic event being the eruption of Mount Mazama or Crater Lake, and that's about 7,000 years ago. And that really produced some of these large pumice plains in the northern part of the basin. Next one. So what exactly is basin and range, for those who aren't familiar? It's where you have extension of the crust kind of at a large regional scale. And so as the crust gets pulled apart, it gets thin, it gets brittle, it cracks, and you develop these big, large blocks. And some of these blocks get dropped down, as shown in here. It's called a graben or a basin. And then there's some of the other ones kind of stay up or even can be uplifted, and that forms the ranges. And what's really kind of characterizes this process is large, flat, broad basins, and then fairly steep sides and kind of higher ranges, and really kind of a series of almost parallel basins and ranges. This is kind of the dominant geologic process throughout much of the western United States. The Klamath Basin being the northernmost extent of this geologic process. So again, like I said, I'm going to focus kind of on the basin and range geologic units. And so these are mostly represented by the purples, either light purples or the dark purples, and then the greens, which are these. The difference here being the green is the sedimentary deposits. So as you have these large basins, you're depositing sediments within them. And then also as you're pulling the crust apart, as you're stretching it, it gets thinner, and that allows for magma to more easily erupt onto the surface. And so again, you see that there's a lot of purple on this map, and that means that there's a lot of this volcanic deposits associated with the basin range, and really kind of is fairly widespread. But then also you have the sedimentary units, and that's, I guess we'll go to the next slide here. So those things kind of happen at the same time, with the sedimentary deposits being more long-term, hundreds of thousands of years of just the same thing happening, and the volcanic units tend to be more episodic. So you can, again, like Mount Mazama, Crater Lake erupting, those kinds of things tend to happen all at once, and they're fairly widespread. But then they may not happen for another thousands of years. But in the meantime, you always have this sedimentary layers being deposited. So this down here represents a cross-section, a geologic cross-section. And if you're not familiar, that's basically like digging a big trench across the map and kind of looking at the face of that. And I want to point out, the green, again, is these sedimentary deposits, and they're throughout much of the basin. And then the purple is the volcanic units, and you see you have purples below the sedimentary units, the volcanic, older, deeper volcanic units, as well as purple above, which are the kind of more recent or younger volcanic deposits. I want to highlight that you have some places where these layers actually overlap, they interlayer, and then also these black lines represent these vertical faulting associated with the basin and range process. So I mentioned that those are kind of the dominant geologic units, and so now I want to talk about how water interacts with those two rock types. So significantly different rock types. Again, one is kind of volcanic. It's more of basalt, lava flows, hard, dense rock. The other is, softer sediments, sand, silts, and clays, stuff like that. And so you can imagine something that's a little more brittle is tending to crack a little bit more, and so you're going to have more open space for water to flow through it, whereas something like a sand or silt or clay is going to kind of squish together a little bit more. And so what we use to describe how well water flows through a geologic unit is this term of transmissivity. And if you think about it, it really just means that it's how well water can be transmitted through the system. The analogy I want to make is it's kind of similar to the insulation in your house. If you have really good insulation, that means your house doesn't transmit heat very well. Whereas if you have poor insulation, it can transmit heat much faster. So again, this transmissivity is how fast water moves through these different rock types. This graph here is, again, taken out of one of these USGS reports. And really each symbol, each square or diamond or triangle represents an estimate of this transmissivity, an estimate of this property from a single well, from either a pumping test or an aquifer test with multiple wells, or even kind of a drawdown or specific capacity test done by a driller. And then what they did was they kind of lumped these into, well, what rock type are these wells producing from? And when you start to compare things at this scale and you start to collect enough data, this represents 262 wells just on this plot, You see that in general, the volcanic aquifer, or the volcanic units, are more transmissive. They can transmit water faster, they can transmit water better than the sedimentary units. I also want to point out here that these estimates of transmissivity, they cover quite a large range. This is a log scale, so it goes from 0.1 to 1 million, so orders of magnitude. I also want to point out that these two units overlap in their transmissivity values. You have parts of the sedimentary system that are more transmissive than parts of the volcanic system. But overall, when you kind of average things out, the volcanic unit is more transmissive. So I'm going through this a little bit fast in the interest of time, but if you need me to stop or go back and talk about something, I'd be happy to. So now getting into kind of the how water moves through the basin as a whole. Where does it go? Where does it start? Where does it go to? This really relates to, where is water coming into the groundwater system and then where is it leaving? So the Klamath Basin is just east of the Cascade Range, so it's kind of in the rain shadow of the Cascades. And really think of it more kind of a semi-arid environment. Klamath Falls mean annual precipitation around 13 inches. And you compare that to the Cascade Range up here at Crater Lake, where the mean annual precipitation is about 65 inches. So a lot more rain coming into the Cascade Range, a lot less rain, a lot less precipitation at the valley floors. But you also see higher precipitation rates along the Basin Divide. So this is the Basin Divide between the Sprague River and the Lost River, and again up here between the Klamath Basin and the Summer Lakes Basin. And so what you can do with that information, what that really does is that's kind of the driver of the groundwater flow system. Groundwater is going to move from the recharge zones to the discharge zones. It's going to move from where you have higher precipitation is going to be higher recharge, and it's going to move to where you have lower recharge. It's just going to kind of follow that gradient. This is a very busy plot, but I want you to just kind of focus on, again, this is taken out of this USGS report. The purple lines represent which way groundwater is flowing. And this, again, is from about 1,000 different wells, water level data that's been compiled. And so, for example, here's the Sprague River, here's the Williamson River. You see that from this side, groundwater is flowing towards the Sprague River. Over here in the Williamson, groundwater is flowing towards the Williamson River, towards the valley. And again, flowing from the high recharge zones in the Cascade Range, down towards Upper Klamath Lake and the Wood River system. But basically, flowing away from the high recharge zones towards the valley floors. So in a cross section, this can be simplified something like this. So you have the higher recharge zones, and you have groundwater moving through the system, here represented as these purple lines. And it's really, the groundwater is moving from both sides. It's higher elevation, higher recharge on both sides, and being concentrated below the center of the valley. And so in places where you have this sedimentary unit overlying this volcanic unit, the sedimentary unit is less transmissive, so in a sense it resists groundwater movement. It's not impermeable, but it means that it's harder for water to move through it. So in order to get water to move through it, because otherwise you're just going to be building up water down here, and indeed you do that, you're building up water and you're building up the pressure in the deep system. And eventually you build the pressure enough to where it's sufficient to drive water through the fine grain or through the sedimentary system up here. And when that happens, you actually have enough pressure to drive water to the surface, drive groundwater back up to the surface, and there it can be evaporated, it can be transpired by plants, it can be captured by streams, and then kind of, basically it gets captured and it gets whisked away along with, and just kind of to join the rest of the hydrologic cycle. And that's the point I want to make. The groundwater system, it's part of the hydrologic cycle. You can kind of think of it as just kind of a detour from kind of the main, going down the streams and rivers. So here again with this plot, but really now I just want to point out what's unique about the Klamath Basin is there's a large number of very large spring complexes throughout the Upper Klamath Basin. This is, again, data taken from some of those USGS reports. And I want to focus on this table here, which shows just an example of some of these springs and what the flows are. And so again, I'm talking flows in terms of cubic feet per second. You see a lot here are on the order of tens of cubic feet per second. And I want to kind of point out Spring Creek, which is located which is located right about here. And again, you see there's a groundwater arrow pointing directly to where the headwaters are. And Spring Creek is, it's only about 5 miles long. It kind of comes out as this large pool, this large spring complex, and flows at about 300 cubic feet per second. And so Ivan kind of talked about the Wood River system, and remember he was talking about 300 to 400 cubic feet per second, I believe, is that right? So Spring Creek just is almost entirely fed from groundwater discharge, basically 300 cubic feet per second. And so if you add, when you kind of look at all of these springs kind of taken together, as well as where you have the gaining reaches, and a gaining reach is kind of where groundwater is just discharging to the stream bed and being taken up by the river. The estimates come out to be about 1.8 million acre feet of groundwater that is annually discharged to surface water. So again, that's 1.8 million feet, or 1.8 million acre feet of water that basically goes through the detour of the groundwater system instead of kind of the surface water system. Okay, so I want to get into kind of a little bit more of the conceptual approach of how these systems work, how this groundwater surface water connection works, especially in the sense of where you have these fine-grained sediments overlying more productive aquifers. So going back kind of from this slide, but kind of making a more simple block diagram of it. Again, recharge at the higher elevations, groundwater flow paths, concentrating below the stream, upward flow. Here I'm representing the sedimentary units as yellow and the volcanic units as gray. I tried making these green and these purple, and the colors just kind of clashed and didn't really work. So just apologize for switching colors. I'm going to focus on just kind of one half of this system because, again, you can imagine it's symmetric on either side. So I mentioned the idea that pressure is being built up in these deeper systems. So water's coming in, and if this was completely impermeable, there would be no place for the water to go. But you would still build up this pressure. And because it's not impermeable, but it's a lower transmissive unit, all that means is you need more pressure to drive water upward through the system. And so the pressure in the deep aquifer then, because it's being confined here, the pressure is building. And the pressure is greater than what you have at the kind of this shallow aquifer near to the surface. And this is where you can have these kind of, flowing artesian wells. So if you drill a well kind of in this sedimentary unit, this is kind of your typical water table well. Water level, you drill a well, somewhere down there you hit water, and the water level is 10, 20 feet below ground surface. Whereas if you can actually drill through the confining layer, through this low transmissivity layer, and into this deeper aquifer, because the pressures are so much higher, there's actually sufficient pressure to push water all the way up above the land surface. And this is how these flowing artesian wells develop. And really, this flowing artesian well is actually evidence of higher pressure and enough pressure in the deep system to drive water all the way up to the land surface. So again, I mentioned this is kind of a water table well, and then this is kind of a flowing artesian well, and these are essentially, you can think of these as two different aquifers. Whereas this water level up here, the height that the water level comes up above the land surface or in this flowing artesian well, or the pressure in the flowing artesian well, represents the pressure at the bottom of the well. So higher pressure, I'm going to represent this by this blue dashed line. We'll call this the groundwater table, or the groundwater level. We'll call this the water table. And now because you have higher pressure in the deeper system, and because this confining layer is not impermeable, there's, just as you have water flowing upward through this well, because it's a big hole, big hole through this upper layer, water also moves upward through the pore space, just through the pore space between the sand grains, the silt grains, and even the clay. There's enough, it's microscopic, but there's enough transmissivity, as we showed from those plots earlier, that you can still move water through it. It's just you have to get sufficient pressures to drive water through the system. Through this system. And this is what we will kind of refer to as diffuse upward flow. So diffuse in the sense that it's happening kind of throughout the entire, throughout this entire margin between these two, this volcanic aquifer and the sedimentary units. And as opposed to like at a very discrete, at a very specific point, like the flowing artesian wells. I mentioned with the basin and range geology, you have a lot of faulting, a lot of vertical faulting. these faults really act in a sense the same way as a flowing artesian well, or as the same way as a well, in that you kind of create this preferential flow path. You create a conduit that allows water to move vertically much faster than it can move laterally. And because you have higher pressures down here, you have sufficient pressure to drive water up through these units and up to the land surface. And faults just provide kind of a more preferential or better conduit to move water that way. And again, that's why we see kind of these abundant springs throughout the Klamath Basin. And a lot of them are associated with these kind of large regional faults. Taking it just a step further, if you have a fault that is, in this case, that is underlying a river. If the river wasn't there, you'd probably see springs like you do over here. But because the springs are kind of coming up the stream bed, this is where you have this idea of a gaining reach. So it's not that, so the gaining reach is really just where there's kind of, springs coming up in the stream bed. And so, upstream from there, you have 20 CFS. Downstream from there, you have 50 CFS. And so somewhere along that reach, you're gaining, 30, 20 CFS. You're gaining some water, along that reach. And it could be from a single spring. It could be from a single fault. It could be from a kind of a fault zone, numerous faults. But really the point is that the reason why this happens is because you have higher pressure in the deep system and you have enough pressure to drive water up to the surface. So the last little bit, talk about kind of getting more into stream depletion. So kind of already hopefully developing a conceptual understanding of how groundwater flows through this system. Let's talk about what actually happens when you start pumping it, when you actually start to kind of perturb the system. So beginning before 1930s even, but late 1930s, early 40s, there were some of the first and more heavily cited papers began coming out about what is the source of water to wells. Kind of the recognition that it's coming from somewhere. It's not just magically appearing. And really, early on, they were able to kind of nail down that, the source of water to wells is either storage, and this is basically, water that's in the aquifer that you're taking out. So in a water table situation, this would be where the water table is lowered and you have sediments that had water in it and now it no longer has water in it. That's kind of taking water out of storage. You have induced recharge, which is where you're actually you pump enough water where you're pulling water into the aquifer that wouldn't have naturally gone in there. And then you have reduced discharge, and this is kind of the opposite of induced recharge, and this is where you're actually pumping enough water that you're slowing down the natural movement of water. So instead of discharging where it was supposed to go naturally, it's no longer doing that. And this is where stream depletion comes in, as part of this reduced discharge. So again, starting with this simple block diagram, but now we're going to actually start pumping. We're going to start changing the groundwater level up here. So the first thing that happens when you lower the water table, or if it's an artesian well, you lower the pressure. When you open the valve, the pressure drops. And that pressure drop represents a lowering of the pressure in the aquifer in the vicinity of your well. So because you have lower pressure now around your well, still higher pressure in the rest of the system, that forces water to flow towards your well and eventually up through the well. Because you've lowered the pressure down here in this system, now you've reduced the upward gradient. Because remember, it's a permeable material up here, but it still requires sufficient pressure to push water up through it. And so if you lower the pressure, you're not pushing it as hard. So there's less water flowing upward. So you can actually reduce this diffuse seepage. You can reduce this upward gradient. Similarly, for these springs, again, these are preferential flow paths. Water moves better along the fault zone than through the rest of this material, but it still requires that pressure in the deep system to drive water up. And so by reducing the pressure in the deep system, you're reducing the amount of water that's going up to these springs. And you're also diverting water, because water naturally would have flowed past your well, maybe discharged to the stream. Now you're actually diverting it, it's going into the well. And this is kind of this idea of reduced discharge. You're actually kind of reducing the amount of water that would have been flowing out of the system, and you're doing that because you're lowering the pressure. You're not actually necessarily taking a drop of water that was in the stream, but you're just getting to where there's less drops of water going to the stream. If you continue pumping, let's say in this example you've actually lowered the groundwater level in the deep system to where you have lower pressure down here, and now you have higher pressure up here, and so high pressure to low pressure. The water is now going to flow from this aquifer down into this aquifer. This is kind of this induced recharge. Naturally the groundwater here would have flowed along this sedimentary unit, but now you're actually bringing it down into the deep aquifer, so you're inducing recharge that way. And again, you're just further reducing flow to springs, further reducing flow to streams. And then finally, if you kind of take this to an extreme example where you've actually lowered the pressure in the deep system, you've lowered the groundwater level such that there's no longer sufficient pressure to drive water all the way up to the surface. So this is where you start to see these dry springs. There's still an upward gradient, but the upward gradient kind of stops when you get right here. There's not enough pressure to push water all the way up to the surface. And so, yes, you start to develop these, or you start to see dry springs. And then eventually, if you get further and further along, you can get to where you've actually reversed the flow direction, the groundwater flow direction. And this can be where you would actually start taking water from the stream and it would actually start flowing back down into the aquifer. And again, this is kind of this induced recharge versus reduced discharge. And then just lastly, to kind of point out, let's say you stop pumping, your water level starts to come back up. But now remember, you've taken all this water out of storage, you've reduced the pressure, and the only way to get that pressure back to where it was, or to fill that aquifer back up, is to basically have water continue to flow into basically the pore space that has been emptied out. And this is what we call residual stream depletion, or residual impacts. Because even at this point, even though you're not pumping, you're still driving water down into the deep system. There's still not the pressure that, in this case, there's just enough pressure to get it back to the surface, but there's still not the pressure that was there before you started pumping. All right, so that's a lot, and it's by no means anything simple. It's very complicated. It's very complicated. Just the physics behind it, the math behind it, as well as trying to understand the hydrogeology. And Steve Gingrich at the Harney study kind of mentioned this, the idea of this kind of numerical modeling technique and how really that's kind of the only way to really understand these things, as a whole system, because it's really difficult, like you said, I think the words he uses to pencil out, what one well is doing to one stream or one well is doing. But you kind of need this kind of conceptual understanding first, and then you can develop these models and collect this data. And if your conceptual model is right, then the more data you collect, the more it'll just kind of support your understanding. So just quickly, the conclusion is kind of hitting back on these main points. Basin and range, geologic province, mixed volcanic and sedimentary units. Volcanic units much more productive, much more transmissive than the sedimentary units. Groundwater flows from uplands, from the higher recharge zones to the valleys. The valleys kind of act as the discharge zones. Water's moving towards the valleys. Pressure builds. It's enough to drive water back up to the surface where it gets taken away by the streams. Faults. Again, these faults associated with the basin and range, they impact groundwater movement, but they don't exclude groundwater movement. Just as the sedimentary units are very low transmissive, low permeability, they're not impermeable. Faults are kind of act the same way. It just takes sufficient pressure to drive water across the fault. And in most cases, in this scenario, it's a lot easier for water to move vertically upward through the fault than to actually move laterally across it. Fine grain pressure, I kind of mentioned this. This fine grain sediments is what allows you to build these pressures. And these pressures are what basically is why you have these flowing artesian wells. Upward groundwater movement can be via this kind of diffuse seepage or the preferential flow paths. And then source of water to wells, intercepted discharge or stream depletion, induced recharge, and storage. And I want to make a point here is that, those three sources are going to be 100% of your pumping rate, but the proportion of them is going to change over time. Initially, you start taking most of your water from storage, and then eventually you'll start taking it from other sources. It's going to change with your distance from your well to a surface water source, to a stream. It's going to change with the hydrologic properties of the aquifer you're pumping out of, as well as the confining aquifer above or below it. Stream depletion, like the groundwater movement, again, these preferential paths, you can have more of an impact to a spring than you would to kind of the diffuse seepage flow. And then I kind of touched on this last part, but and again, Steve Gingrich pointed this out, this complex geology, complex hydrogeology really kind of requires these kind of advanced techniques to really understand it at a basin or sub-basin scale. So my last slide, I just want to have to have a picture of rocks there. So this is a road cut actually in the Klamath Basin. This would be representative of the sedimentary unit. And I want to point out a few things. First, you see this is about 10 feet, so maybe about 50 feet long. first you see that it's not all the same color. There's a lot of homogeneity in here, heterogeneity. You have different layers representing different sedimentary environments. Silts, sands, clays, there's chalk, there's going to be some chalks in there, some gravel. Again, just a homogeneous material. You also have, you see this layer is kind of offset, that's one of these faults. And it's a very small one, but you see the offset maybe a foot or two. And then if you see over here, you see kind of this sawtooth pattern. And that, even in itself, is these small, maybe inch or two faults. Not a lot of offset, but still just adds to the complexity of this system. And so kind of the thought experiment then is like, try to imagine where a drop of water would flow through this system and how it's going to impact by this layer versus this layer, this fault, and so on. And then, of course, try to imagine doing that at 10,000 square miles. Thank you.
Thank you. Who's got any questions, comments?
Yes.
Go for it.
One has to do with precipitation projections going forward. I think you had your precip totals contrasting the Cascades and the Klamath were 1960s to 1990s data. Did I catch that right? I guess we don't know.
1961 to 1990.
Here we go. So those are means.
Yep.
And I'm not familiar with the projections for this area as much as for the West Cascades, where the projection is pretty clear that volumetric precipitation is not projected to change too much, but seasonality and therefore form. Much less snow, much more spring rain. Are there similar projections for the area? 1990 was a long time ago already. And then related to that, given the form of precipitation that's the source of that pressure, is that projected to change with change in precipitation? Will there be less pressure or more pressure to rely on with water coming from the source up high?
Chair Reeves, Commission, sorry. I'm not a climate scientist, so it'd be difficult to answer that first one, but I think, Ivan kind of highlighted that, in the last 10 years, we've had 6 droughts, so, clearly, at least in the last 10 years or so, there's been, less precipitation, and I think certainly along that line, you're going to have, warmer temperatures, less snowpack. The snowpack is kind of what persists, or what allows the precipitation, the water to persist throughout the year. Again, I'm not necessarily familiar with what the projections are going to be. But then as far as the impact to the groundwater system, I think certainly. I mean, I think, the less recharge into the groundwater system is going to affect, how much pressure is down there, how much water is moving through the system. To kind of, I mentioned this, kind of the groundwater system, kind of a detour on the hydrologic cycle, and I was just looking at this up earlier. So I said about, right around 2 million acre feet of groundwater discharged annually. Total estimates for precipitation are about 10 million acre feet. So groundwater makes up about 20% of that. And so, so whatever your change is going to be, the groundwater is going to see about a 20% of that. So more of your impact is going to be, I think, to the surface water source or surface water system. But certainly, try to point out they're a connected system, and so, your groundwater component or your groundwater impact is going to be probably a little bit, it's going to be less than that, but I mean, again, on a conceptual basis and a kind of like a physical basis, it's going to have an impact for sure, but how quantifiable that is and how noticeable that is, I can't answer that.
And then one last question. Is it fair to say that at the very end, your last slides there, where you're showing the impacts of withdrawal, is it fair to say that most of the dissatisfaction in the basin, most of the argument brought in the lawsuits has to do with that distance to impact? That we're going from, what was it, wells within a mile connection to 500 feet? Is that what I heard?
Chair Reeves, members of the commission, the distance is a little bit hard to discuss quickly. Under the Division 25 rules, we utilized the term gaining reach, where as part of this study and additional studies that were done out there, Water Resources Department staff, USGS staff, other professionals over the years mapped specific stream reaches that had measurable gains in surface water associated with them. So instead of a direct measurement between a well and surface water, we measured between a well and the nearest gaining reach. Well, that is what took a bunch of wells off the list subject to regulation. There were only 50 wells that were functionally within a mile of a gaining reach and had an effective and timely component to them there. There's a fundamental debate, if you will, between, I think, the agency and the water users in the basin. I think from our perspective, we might try to get at this. The presence of a confining unit, confining sediments, a confining layer does not stop groundwater from being hydraulically connected to surface water. That's a very common misconception probably across the planet. One of the USGS circulars calls that out specifically. So these are not impermeable units, layers, or sediments. We haven't found an impermeable layer out there yet. And so this hydraulic connection issue exists, and eventually there will be a response. There is uncertainty as to exactly where the response occurs and when the response occurs, and we don't deny that in any way, shape, or form, but the agency's position is that groundwater is connected to surface water, and pumping wells eventually deplete stream flow. And we're certainly open to new evidence to be provided to us, but there's a vast body of existing evidence before us and nothing to the contrary there to show that, show lack of connection. So, thank you.
And so if I may, so the answer to your first question, how will changes in climate affect the system? I think that's exactly the kind of question that you can ask a numerical model. Once you develop this model, you can start saying, well, what if I one of the inputs to the model is going to be precipitation. You can say, well, what if I change that? What's going to happen to the rest of the system? So.
Well, I think you may have answered my question, maybe totally. I really want to know the difference. Why the rules for 690.25 would only generate 50 wells that would have to be regulated, and now in 690.009 it's 140. I think you've explained that in Joe's answer, so thank you.
All right. So we have requests to do for public comment on this agenda item. I'm going to go ahead and start that unless you have any last questions. Okay. So what I'd like to do, given the time, we're a little behind and we have another agenda item next. If the commenters in this agenda item could try to keep their comments to 5 minutes, we would appreciate it. Brandon Topham.
Hello, Chairman and Commissioners. It's nice I recognize most of you from the last time you saw me this last summer, and at that time I was actually wanting something, rule change, and some people, you're probably wondering if I approve of these rules or not, and the short answer is I probably should. It's going to allow me to irrigate for the next 2 years. That's always a good thing. Problem is that it's going to essentially kill our ranch after that. The rules.
Chair Eves, can I interrupt? I'm sorry. Brandon, are we clear that this isn't testimony for the new rules yet?
That's correct.
Okay.
Okay. Yeah, and that if you do, the important point is if you want this on the rulemaking record,
I'll be speaking again in a
Okay.
minute or two.
All right.
I wanted to speak at this time to allow you guys to interact with me.
Okay.
And I seem to have misplaced that particular rule page. Bah. I was hoping for a little more time to get my notes in order, but anyway, the new rules essentially connect all surface water. It implies that all groundwater and surface water is connected, and then goes on the assumption from there on. And they keep citing the 50/50 report. So I sat down in the last 2 nights and I read that whole damn thing, and it never in that whole document does it say that all surface water and groundwater is interconnected. That statement is not there. And if you want to read the 50/50 report, there's a lot of things in there that the Water Resources either misleads or, I don't know if you could say lies, but definitely misleads. So, they talk about upper basin. And that report, its definition is the upper basin is everything from the from the Iron Gate Dam up. Just a few minutes ago, they were just telling you that was the Copco Dam up. That makes a pretty big difference in your river flow. But even that isn't particularly relevant because these rules only apply to Klamath Lake and above. Most of the 50/50 report is actually focused on the Klamath project. They've got some serious problems down there, especially after 2001 and they drilled all those wells. There's something to be said for their problems down there. They were talking about the 1.8 million feet. That's not the water going into the Klamath Lake. That's all of the water going, 1.8 million acre feet from groundwater is what they talk about. Let's read what the 50/50 report. An estimated 1.8 million acre feet per year of groundwater discharges into streams. Discharge to streams occur throughout the basin, but prominent areas of groundwater discharge include the flanks of the Cascade River, margins of the Wood River Valley, area near the confluence of the Williamson and Sprague, the upper Williamson near Yamsey, Bonanza Springs, Lost River, and Klamath River Canyon below John C. Boyle. So if they were going to give you some numbers, why didn't they give you the numbers for the relevant area? They got you some damn big numbers, but I'd be interested. What is the numbers that are actually relevant to our area? And I could go through here, and there was another probably 5 or 6 things that was said today that I could take their own USGS document and flat out disprove it with their own USGS documents. Ivan Gall was talking about going forward. Going forward, he wants to come down and communicate and educate us. How about doing some research? Throughout the 50/50 report, it says in multiple places where it doesn't know much about the Sprague River Valley. It doesn't know this number. It doesn't know that number. Admittedly, I have not read their computer model one. I was kind of short on time this last few nights, but so maybe the computer model, they think they can answer it with a computer model, but if you remember earlier, I was wanting you guys to pass a law, just change Division 9, add in a thing in there that says aquifer tests trump computer models, and I'll go home a happy person. If you can do that, I will be very happy. Joe, I believe you were the one that was asking what the main debate is or something like that. The main debate ultimately is that yellow the slide with the yellow in the middle of it. The main debate is how much water goes through, it would be one more back or forward.
This one?
There we go. Main debate is right there. How much water goes through that yellow stuff? There are studies, some of which are cited in the 50/50 report, but they did not cite that particular part that I'm going to cite, that says that there is no water that goes through that before man came along and drilled wells. They were talking about gaining reaches. He talks about the diffuse discharge going up through the stream bed there. Shouldn't that make there should, if that is true, you measure the stream upriver and you measure the stream downriver, there should be a difference between those two numbers. There should be however much water is coming up through the stream bed. In the 50/50 report, they're happy to tell you about large reaches where there is no water is coming through there. There's a 25-mile reach here. There's a 10-mile reach here. It's about half the reaches do not have any measurable gain. I'm sure I've got other things, but I'll save the rest of whatever I got for the other part if anybody has any comments.
Questions, anyone? Thank you. See you in the next agenda item. Tom Mallums? And if you just say your affiliation, if you'd like to.
Thank you, Madam Chair and Commission, for this opportunity to ask some questions or to give you some input and to hopefully have some interaction here to ask me questions also. I'm here representing the Oregon Cattlemen's Association and myself as an irrigator in the Klamath Upper Basin. Some of these things have a very deep-rooted problem with any regulation in the Upper Basin. I will reference a 1990 letter that was sent out to all irrigators in the Klamath Basin on the adjudication, the surface water adjudication. In that report, or in that two-page letter, in the bottom of page 1, it says if you are a groundwater irrigator or a municipality user of water, you will not be a party of this proceeding. In other words, groundwater users were denied their total due process. Now we are being shut off, including cities, of their water, well water, under a surface water call. And that seems to be extremely inappropriate under Oregon water law or any basic law. Whereas in this actually specific rule that we're talking about now, why is there no requirement of site-specific science? That's been one of the biggest issues on this issue here completely. They're completely happy with using a model which is nothing more than a theory. And that theory has lots of holes in it. And even Mr. Toma acknowledged they don't know a lot about the hydrology here. There's a lot of unknowns. Why don't they use the actual science that is out there? There have been wells tested. They have that information, but yet they refuse to use that in changing their modeling system. I think you asked Mr. Moll, I believe it was you that asked something about how, what if this and what if that in the modeling? Well, expert modelers have tried to redo their modeling, and they can't make it work because their modeling picks and chooses what kind of data they put into it. And experts at modeling will tell you they can be manipulated in a heartbeat. They actually say garbage in, garbage out. And I think that's what we have here in many cases. I'm not saying their model doesn't have some relevance, but the way it's being used here is totally nonsense, to be honest with you. We met with Water Resources back in, I think it was January of 2018, and tried to get some clarification on what it would actually take to shut off our well. And I actually gave them a hypothetical. If I drilled a well 1 mile deep and was 10 feet short, I think, of being a mile away from the waterway, would you shut us off? And the answer was yes. Now, common sense, I'm a nuts and bolts kind of person. That makes no sense. And they actually told us that all our model has to do is to show that there might be a chance that our well would prevent 1 drop of water from getting to a waterway. 1 drop of water. What happened to timely and effective? And with that kind of a model, with 1 drop of water being the parameters, you can't prove that, really, one way or the other. You can't prove a negative. So, in essence, we've been deemed guilty, and we can't prove ourselves innocent. How does that work in our Constitution? It's very disturbing to me to have to prove my innocence as an irrigator when they should be proving us guilty with the preponderance of the evidence. And their evidence is a computer model that has many, many flaws. I will point out another flaw that was, and I wasn't in the courtroom when this happened, but we looked it up in some of the transcripts. Carl Wozniak was their expert witness on modeling and some of their hydrology in a recent court case, and he mentioned that, or he was asked the question, I think, why they're using the Hunt model. It was a specific model on the being able to shut off the water. And he said, that's the best one we have at the time. And somebody asked, why don't you use a USGS model? And his comment was, the USGS model was very inappropriate to try to even use in the Klamath Basin, the Upper Klamath Basin. It would be inappropriate. In 2018, Water Resources changed from the Hunt model to the USGS model. So their own expert says it's improper to use it, but now they're using that to shut us off. That's extremely disturbing. We talked about the USGS model, or the USGS report from 2007, and they say, well, yes, it says there are no confined aquifers in the Klamath Basin. I think Brandon touched on this a little bit, but that report does say that there are compartmentalization aquifers with impermeable boundaries. That's, I think, the very definition of a confined aquifer. In the same report that they're using to disprove, they're cherry-picking what kind of information they're using. And that is extremely disturbing. They say in some of their reports, this 8-page document, a memorandum that Ivan Gall presented, that their information has been peer-reviewed according to USGS standards. USGS standards actually says if there is a financial consequence, they have to have a higher standard of peer review. They aren't doing that because there is a huge financial consequence here. The Klamath Basin has a somewhere between $600 and $700 million ag industry. A lot of that is in the upper basin. That's all at risk here. And remember, those are at like 2013 figures too. Now I'm sure it would be more than that. To say there's a financial consequence is kind of the understatement, but yet they aren't doing the extra peer review that is required by USGS standards. Division rules, this interim rule in the two different places it says, well, it's supposed to be for the upper Klamath Basin, but in two different places it says in the Klamath Basin, groundwater and surface water are connected with no definition. I've been a member of the RAC also, had the two meetings. In the second RAC meeting, Mr. Gall said, yes, the Klamath Basin means the entire Klamath Basin. But these are rules for the upper Klamath Basin. They're encroaching on the rest of the Klamath Basin and going to swallow up those wells also in this type of a rule. I think most everybody that I talk to believe that this interim rule will become permanent. It will be melded right into a permanent rule in 2021. If that language is in there that blatantly groundwater and surface water is hydraulically connected, the entire Klamath Basin is at risk. And that's not acceptable. It's just plain not acceptable. There are some things that are not defined in these documents. And another one that I don't have any real documentation on this one, but the experts from Geosyntec said that the way this rule has the definitions in there, it has the potential to open up over 380 DEQ contamination sites within Klamath County alone, because this rule says groundwater in the Klamath Basin is connected to surface water. Those sites have been settled somewhat time back, but this opens up a Pandora's box that says, gosh, somebody can sue the current landowner, DEQ, or who knows who on a third-party litigation. I mean, the sky's the limit here. And that's a huge financial impact for the state of Oregon. Now, Water Resources they've openly said, yes, they've had some extensive litigation going on here in the Klamath Basin, and I agree with that. We've been part of that. This last biennium, they've spent their $836,000 of litigation funds, and that was depleted. They asked for and got another almost another $1.4 million, and that will last until June, and they're now asking for another $1 million. How many wells could they have actually tested in the Klamath Basin to see if their model even works? They have tested not one single well in the Klamath Basin to see if their model is accurate. We have tested a number of wells with a geohydrologist, PhD, and they discount that information. Their model is better than on-the-ground site-specific science. I feel that is extremely inappropriate. We're talking about hundreds and hundreds of family farm operations, of which ours is one. 5 generations that have been working for generations and generations and generations. this could be the end of that. And we're not the only one. There are many of those multi-generational farms and ranches that their livelihood depend on being able to pump this groundwater. Back in, I think the first time when we got our surface water right in the late 70s, we were told, a wells can be drilled, but we decided to go surface water. In 2001, after the water shut off in the project, we were told, drill a well, your water will be safe. That didn't work out very well. Many others, way back even before that, had told people in the upper basin, drill wells and you'll be safe. Drill wells and you'll be safe. Well, that's not the case. That 1990 letter says it all. We weren't a part of the state surface water adjudication, but now that's going to hang us out to dry, literally dry. And that just, in the state of Oregon, I expect better than that. Water Resources in the past had been a very strong ally of irrigated agriculture. And over the years, that has changed drastically. And I'm really sad to see that, because we've had a very good working relationship years ago. It's deteriorated where there's very little, if any, trust in the department. And it's nothing really, I won't say personal about the individual people, but they aren't following a lot of the laws that are on the land. And I was even told that some of the laws of the land don't necessarily jive with policy.
I'm sorry, Mr. Malma, I don't intend to be moot, but I do have a question. Is it okay?
Yeah.
Oh, yes.
I'm sorry, it sounded like you were also representing the Cattlemen's Association today, is that correct? So when we discussed this a year ago, and I plead great ignorance in terms of the decisions that are made by an operator on an annual basis related to water, but one of the things I heard last year was that decisions about the number of cattle to be leased from outside the area on land in the Klamath were made based in part on water. I'm curious, and it's a heavy ask. I'd be stunned if we had good data on it. But from the last grazing season, do you have good numbers on how operators shifted their operations? Were fewer cattle brought into the Klamath? More cattle sent out? Do we know much about how individual operators collectively adjusted to the changes?
Yes. To my knowledge, I've been told about 50% less. 50% I don't have, that's not a rock-solid number. Others in this room would probably have a better knowledge of that, but I've been told approximately 50%.
Thank you.
And because you can graze on dry land ground,
right,
but if you don't get rain, you're dead in the water.
Thank you.
Any other questions for Mr. Malum? Thank you for taking the time. And if you want to speak on the rulemaking record, you should come back in the next.
Yes, I plan on doing that also.
Okay.
And thank you very much for hearing me out. And I really encourage you to ask questions, because this is a very complex issue, and that's part of the problem here is they seem to be okay with using a computer model, a theory, to shut us off and to destroy our livelihoods, to where site-specific information should be required on any rule all across the state. Thank you very much.
Thank you. Dominic Carollo?
Chair Reeves and Commissioners, thank you for the time here. I'm here on behalf of a number of irrigators in the off-project Upper Basin area. So the two parties they listed there is Fort Klamath Critical Habitat Incorporated and Sprague River Resource Foundation Incorporated. Those two organizations are dedicated to sustainable agriculture in the Upper Basin off-project area. They have dozens of members, probably all told represent tens of thousands of acres in the Upper Basin off-project area. Many of these same people I also represent as parties, as claimants in the Klamath adjudication. And I'm also here on behalf of a few other clients, including the Mosby Family Trust, who are in the Upper Marsh area and who otherwise aren't members of those two organizations. But it's sort of I'm speaking on behalf of those folks here briefly about a few of the things that were mentioned in the slideshow, and then also about the rules. I was planning on just testifying later, but there's a couple things here that I wanted to address briefly as well. So The first thing is the slide here, I'd sort of be remiss if I didn't address the slide they had here about increased regulation in the Wood River. I wonder if you could call that up really quick. So one thing I wanted to point out is Mr. Gall is suggesting that what you're seeing there is the disparity between the tribal in-stream flow and that in-stream claim level and the actual flow. The thing I wanted the commission to be aware of is that during those 2 years when you see that disparity in 2015 and 2016, we had the reduced stream flows that were agreed to under our settlement called the SIF levels. And so we weren't actually, those claim levels weren't in full force and effect, and the stream levels that were enforced were much lower, and that's why you're seeing the stream levels being a lot lower during those 2 years. And on behalf of the Fort Klamath irrigators in that basin, I just wanted to tell you that, I mean, they take their obligations very seriously about regulation, and we were working together with the tribes and Water Resources to make sure that those SIF levels were met in 2015 and 2016. And so I thought it was very important that the commission was aware of that information. The reason why those claims levels were in full force and effect in 2017 and 2018 is because those low reduced stream flows weren't in effect due to the breakdown with the settlement and the ultimate termination of the settlement. So anyway, just word out there for my Wood River Valley irrigators. Yes, sir.
Didn't part of the discrepancies and all that there, we got to remember the hydrological years. 14 and 15 were severe droughts. 16 was a very good snow year. 17 was a very good snow year. So we had different, the flows were partially not met and met because of the situation of the years we was in too. Is that not right?
Well, it's true, but actually that was one of the things we incorporated into the settlement we had was that actually the SIF levels, the stream flows would actually be lower in those drought years than they would be in the plentiful water years. So they were an adjusting stream flow level that we had under the settlement. So actually the SIF levels accounted for those drought situation in setting those levels. They're kind of custom set for each month. And again, I mean, the parties worked together to make sure that those stream flows got met. So I just wanted to make sure that the commission was aware of that. Separately, I want to touch briefly on this issue about the Division 25 rules. It was 10 of my clients in the Sprague River Basin that filed 10 individual lawsuits against the Water Resource Department over the regulation of their individual wells under the Division 9 rules. And Commissioner Malt, you asked a question about what that was about. And what was different about those lawsuits that I think the commission should be aware of is it really is about, it's about statutory authority and it is about due process. If you look at the Division 9 rules, the two statutes that are cited under Division 9, the first one is the Critical Groundwater Area Designation Statute. The second one is the Defective Well Statute. Those are the only two statutes that are referenced in Division 9. Now, it's true that in Oregon there can be conjunctive use regulation where you regulate groundwater in favor of surface, but in a critical groundwater designation, that may only occur after providing affected people a contested case. The legislature mandated that due process to occur so that things like this model could be vetted, peer-reviewed, and disputed in a formal, contested setting. And similarly, when the department enforces things under the defective well statute, they normally provide parties a notice of violation for their defective well that's interfering with surface or otherwise defective, and they are also given an opportunity for a contested case. So what really happened in 2018 is you had 140 people, and they had a card show up on their door and said, "You're off. Turn off your well." There's no, you're shut off today. You do not get an opportunity for due process in a contested case. You are forced at that point to have to go to circuit court if you want to do that. So the basis of our lawsuit, and I won't get into it, I'm not here to litigate those lawsuits, was simply that that's not the way the process is supposed to work. You're not supposed to be guilty until proven innocent. And that's reflected in the statutes that govern conjunctive use in the state. So I want to make that clear and that the commission is aware that that's a major concern. That being said, we dismissed those lawsuits as part of a settlement with the department because we supported them trying to come up with a different approach to groundwater regulation. We have a number of concerns about the proposed rules, in particular the scientific findings. We don't think those have any place in the rules. But nevertheless, You're going to hear from three of my clients today, Kevin Newman, Roger Nicholson, and David Mosby, that we do support the department's ultimate approach here and support the department's proposed rules, primarily because the rules do sunset and primarily because they indicate that they will not have precedential effect going forward, because ultimately there are a lot of disputes about statutory authority and about the science. Lastly, I just want to briefly state that with respect to what the core nature of this dispute is, a lot of what you saw in the slideshow talks about hydraulic connection. And even if we assume that there's an agreement, that there's some level of hydraulic connection between some aquifers and surface, that's not the question for the purposes of regulation. The legal question is whether there's substantial interference, and in a manner that if you turn that well off, there's going to be timely and effective relief given to the surface water source. You heard Mr. Gall say that if you pump enough, eventually you're going to get depleted stream flows. Again, even if we agree with that premise, the key here is whether or not shutting off this well is going to provide timely and effective relief in the stream. And again, these cards that people got last year, it doesn't prove that. It doesn't say anything about that. And if you look at the regulation on this the department has on substantial interference, the regulatory definition of substantial interference requires that the cone of depression reach the surface water source, or that there be enough pumping that you do have the groundwater flow does recede to the extent that you're now removing water from the stream. There's nothing in that model that demonstrates that any particular individual well that's occurring. And I want to give you this final example. Of the 7 wells that they expect would be regulated under these rules, one of the 7 is owned by the Brooks family in the Upper Sprague River Valley. They'd had seepage runs done on their well, on their stream by the department, found that it would not provide timely and effective relief based on the former Division 25 rules that took into effect whether it was a gaining reach or not. Would not be regulated. But yet under this rule, it would potentially be regulated if the department finds substantial interference. What I would submit to the commission is that if they should direct the department that the 7 wells that are subject to this, that would be subject to this rule, that the department offer them the opportunity for site-specific testing. And we're only talking about 7 wells here. All we're talking about is about 7 wells to ground truth about whether they're actually taking from the stream. And that should occur before they're regulated. And I think that would be a fantastic way to try to use this as an opportunity to understand more about what's actually happening as opposed to what's being predicted in a model. So I'm happy to answer questions, but that's what I wanted to share with the commission.
I just wanted to clarify one thing. Are you thinking that the testing would demonstrate that there isn't a hydraulic connection, or that it wouldn't create the timely and effective relief that you were talking about?
I think it depends on it could depend on the well. It could be both, but ultimately, I think I heard the word microscopic transmissivity. I'm not sure if I can quite use that word. I'm a lawyer, not a scientist. So, there's a huge difference between the pressure you're getting off an artesian well and those return flows that are going back to the river and microscopic transmissivity that you might have in a stream reach that's in proximity to a well. And so that microscopic connection between the stream and the 700-foot deep aquifer, it may not be significant enough for there to be any substantial interference. And that's what's required before they can be regulated. There has to be substantial interference. Certainly we have statutes that were passed by the legislature in the 50s that recognize when they're passed that we need a groundwater act because we know that there's the potential for connectivity between surface and groundwater. But they didn't say that we're just going to regulate every well as if it's a surface water source. That's not the way it works. There has to be substantial interference. And again, there has to be due process according to those people that invested in that supplemental source of water to back up when surface water is not available. They had to have due process before the determination of substantial interference was going to be made. Again, this process of guilty and proven innocent is something that's not going to go away if the department doesn't come up with a better solution.
Chairman, maybe I could ask this to Ivan, because I think I'm getting confused here. Do we not have a testing program for groundwater levels in the Klamath, similar to like we have in Harney? Or do we? Or have we had a testing program, or have we not? I guess I thought we had.
Chair Reeves, Commissioner Korn, I think you heard a few statements earlier from folks that the model was just, my words, based on speculation. There's multiple levels of data included within the construction of the USGS groundwater flow model. The data plot that Mike Toma showed with all the transmissivity information from the sedimentary unit and the volcanic unit, all of that data is incorporated into the flow model. Well locations are incorporated into the flow model. The geological formations gleaned from the well logs are incorporated into the flow model. Aquifer tests, where they occurred. So when you do a well test, that means a lot of different things to different people. That's a couple-hour conversation. An aquifer test is a pumping well, multiple observation wells, data collected over days before, during, and after the pumping phase. It's no small endeavor. That information is incorporated in. The precipitation data is in the flow model. Evapotranspiration estimates are in the flow model. Surface water discharge information is in the flow model. Spring discharge information. There's nothing but data in the flow model there. So with respect to water levels, there's a number of wells in the Klamath Basin, I don't know off the top of my head, that we currently monitor and measure water levels on a quarterly basis. The U.S. Geological Survey measures water levels in wells in the Oregon part of the basin as well as the California basin, part of the basin there as well. During the basin study report, as the guys are doing in Harney now, a lot more wells were located, measured for water level information, and then tested for water quality on a very small number, I'm sure, as well as the pump tests or aquifer tests. So,
Thank you.
If I may, Mr. Corolla, to grossly summarize what you've told us, if I've got this right, you question the science, the due process, as well as the policy or metrics we're using, if I understand that right. But my question to you, with all that said, are you willing to work with the department to at least attempt over these next 2 years more common understanding, and you and your clients willing to provide more explicit information on your thought process and recommendations for moving forward over the next 2 years?
Absolutely, yeah. I mean, I think that's how we got to this point with respect to my clients. I mean, we had 10 lawsuits that we settled expressly on the basis of the department starting this process. So, yes.
Thank you. And to be really in play, Brett, I forgot your last name, sorry. Brandon? Are you willing to do the same thing?
Same thing as what?
To work with the department to try to understand a common understanding.
Interest in working with us. Multiple people have given them aquifer tests that showed something different in their computer models and they've been ignored. I hope they will change their outlook and start working with us, but thus far, it's computer model or nothing.
And perhaps you can help me and explain what the department intends to do over the next 2 years. I would assume that there'd be an attempt for interaction to reach a common understanding.
You asking me?
No, I was asking Ivan, I'm sorry.
Chair Reeves, Commissioner Baumgartner, the intent is to spend time with water users in the basin, and please remember there's both junior users and senior users here that we're dealing with. Trying to get to some common ground. It's my hope, I come from a groundwater science background, that we can get to at least a shared understanding of how the basin physically works. I believe that to be vitally important for all of us as we look at long-term water management decisions in that basin. If we don't honor the way the system physically works, then when we make decisions on how to manage it, things may not go as planned. It's fine to acknowledge a high degree of surface water and groundwater connection. In my mind, that's the science in the basin hydrology. The policy decision is, so what do you want to do about it? To put things in perspective, based on the model, the wells located within a mile of the universe of the 140 or so that we're talking about here, if they pumped for the irrigation season, are estimated to have an impact on surface water. So this would largely be the Wood River system, the Sprague, and the Williamson, of about 90 cubic feet per second as you approach the end of the irrigation season. Compare that to over 300 cubic feet per second of surface water rights on the Wood River alone, 1,200 cubic feet per second of surface water rights on the Sprague River system alone. I don't have good estimates for the Williamson River, and it's a complicated system there. But between the Wood and the Sprague, there's 1,500 CFS of diversion rights that are also subject to regulation and do get regulated. And those provide immediate measurable relief to the senior user. The groundwater that we're talking about is about 90 CFS of estimated impact that is important water to the senior determined claims. But I think it helps put things in perspective. So a policy call can be, we don't regulate wells in the Klamath Basin. And that comes at the expense to the senior users of about 90 CFS based on the estimates. That's not a science call. It's important to understand the science, so when you make that decision, you understand the impact to the senior user. The flip side is that 90, or the pumping wells is very important to the agricultural community in the Upper Basin. It does provide a lot of economic benefit to those folks up there. So, but that's a policy decision, not a basin hydrology decision.
Thank you.
Okay. So I think this concludes, thank you, Mr. Curl, as well. And you guys as well, Ivan and Michael, and Justin, wherever you are. This concludes this agenda item. We're behind schedule, but let's start the rulemaking hearing at 4:15. A reminder that people who want to get on the record in the rulemaking hearing, one of these colored items to go to. No?
The time in which they had to sign up has already passed.
Oh. Per something that people knew about? Okay, so we already have people that are signed up. How many people do we have? Just thinking about how long to expect the hearing to take. Okay, all right. So let's reconvene at 4:15 then, and we'll get underway. Thank you.